Ashish, good morning.
Oh, good morning, Vamsi. How are you?
I'm fine. I'm fine. So you were 20 minutes before.
Yeah, so I was told by an email that I have to join the meeting 25 minutes earlier.
Oh, sorry. I don't know. Just now our plenary talk is finished.
Oh,
Uh,
okay. All right.
yeah, I should have attended that. Professor Ramurthy Ramesh, you may be aware
Okay.
of
Yeah,
ferroelectric.
yeah, yeah.
Yeah,
Yeah, yeah,
yeah.
yeah.
It was nice talk.
The morning was difficult. I had to get children's homework done, so we were just sitting there and
Great, great. So you are spending early morning for the home. Yeah.
well, for the children, the school is on Zoom in the morning, so you can't help.
Yes, yes, yes. That's what I also find difficult this with the online classes.
Yeah, so managing time becomes really very tricky.
Yes, yes.
So should I join after a while or?
Maybe that's what I'm thinking. If you have anything, I think maybe 4 or 5 minutes before is fine. I will try to get Professor Vikram Kumar. Sir should be available.
So
Uh,
let me just try sharing my slides once. Just
yes, yes. Please, please do that.
yeah, let me just try that if everything is working all right. Um, is it working okay now? Can you see?
That's what. Just it's going to appear. I think. Yeah, yeah. We can see that.
Okay, all right. So if I put it in slideshow mode, then do you see the slideshow mode?
Put it. You are already in the slideshow.
Just 1 second. Yeah, yeah. Is it
Yes, yes. It's fine. Perfectly fine.
okay then? Okay, okay. So it's
So
working.
this
I'll join.
basically, I think people who are directly live telecast to YouTube, so anyone can I think watch this
Okay,
also.
all
Their
right. Okay,
recording. So you can come back after now 10:38. So maybe
yeah.
10:55.
Okay, all right. Okay then.
That's fine. So we checked it. So now it's fine. Huh?
Okay, all right. See you then. Bye.
Thank you.
అతని ఇంట్లో ఉన్నారు. చెప్పిందా నేను చెప్పిందా నిజమా ఏంటబ్బా
Good morning, sir. Okay, sir. I just thought that maybe you have any difficulties. Uh, yes, sir. Professor Ashish Kirk and Professor Ken, from Korea. Three oral presentation. Three or four. Sir, 15 minutes. Right. Sir. I will once I will tell you exactly. Is it after 20 minutes? Because I will just. Sir, half an hour, sir. 30 minutes. Yes, sir. Right, sir. And you have the CV of Professor John Dante. That's the oral not required. Yes, he already gave the certificate common for it. He already tested. You all right. Shrestha? Hello, Shrestha? Shrestha, are you there? Yes. Good morning, sir. Professor Garg joined.
How are you?
Hello, Professor
Yes,
Kumar.
yes.
How are you? Good morning.
Good morning. Good morning. Good to see you again.
Yes, long time. We used to have lunch in the lunchroom of ICE quite frequently.
Some time ago, we met in Bangalore last year.
Yes. After that, we met in Bangalore.
Of course.
Yes.
So,
Because of COVID, we are at lunch club meetings.
Yeah, it's a bit of unfortunate
yes,
situation.
yes. Lunch club. And also, conference. We have to arrange. I have to go on before starting.
In fact, I met Sir in a lunch club
Okay.
in 2010. So Sir meets and talks very patiently with all young faculty every day and advise what to do.
Okay. So is it time now? It's still 4 minutes.
Uh,
4 minutes.
yes, sir,
7
two
o'clock.
minutes to go. Yeah. Sir, are you able to see the chat box, right, sir? Yesterday, even day before, you were there in the session, and you have any difficulty see the questions, sir, in the chat box?
In the chat box, I did not. Neeraj Kare
Oh,
was, he
so
could see. but I did not see the.
Professor Garg, so you maybe monitor. Are you able to see the question box, suitcase, briefcase, something?
Yes, I can see the chat box. Yes.
Okay, okay.
No, I could see the session I chaired.
Ah,
There
there
were some questions. The chat came to Professor Khare and he asked them.
today. So
Nothing
morning
came.
you attended, sir. Professor Ramesh talk you attended, sir. Morning.
No, I attended.
No, today morning. Sir.
Yeah.
Sir.
Helper from Singapore, he did the same. Okay.
You can share Professor Garg now.
Okay. All right.
Okay. So, introduce Professor Garg. Okay.
Yes, sir.
Shall I
Yes, sir. You
give me
please.
signal when to start?
Yes, sir. You can start now, sir. You can introduce.
Yeah. Okay. Well, welcome participants to the session on uh, energy harvesting and solar cells. So the first block the four presentations today. My first speaker is Professor Icee from IIT Kanpur, Department of Material Science and Engineering. He has a PhD from University and uh, several awards and fellowships in MRSI also, and Manna Fellowship, Young Scientist Award, and so on. Yes, several patents and lots of publications. It's at IIT Delhi also a few years ago. So I welcome Professor Shishkar to make his presentation now on perovskite solar cell with so Ashish. Go ahead.
Yes. So, Professor Vamsi, shall I keep my video on or shall I turn it off for the sake
Yeah,
of
yes, you should keep so it will go to one corner automatically. So in the
All right. Okay.
audience can monitor.
Okay. Okay. All right. So, thank you, Professor Kumar, for your kind introduction. Good morning, everyone. I first thank the organizers, especially Professor Vamsi, for giving the opportunity to speak here. And it's rather bizarre that we have to talk on this online forum, but nevertheless, we must make use of the opportunity that is given to us. So today I'm going to talk on developing perovskite solar cells with improved lifetimes, which is a very important question. And this is a topic plague the commercialization of perovskite solar cells. quite significant. This work was done by my student Rahul Ranjan, and he is co-advised by Raju Gupta and myself, and with some inputs from Professor Kanwar Signalwa. So let me now. So before I move forward, let me acknowledge the funding agencies: Department of Science and Technology, India, Sunrise, which is Sunrise Consortium of UK under GCR for support like PPSRC, and most importantly, the students and postdocs contribute to our day-to-day activities and all the important results they get for us, and all the collaborators in India as well as in overseas. Let me first give a brief introduction to perovskite solar cells. Perovskite solar cells have emerged from the predecessor DSSC or dye sensitized. Dye sensitized solar cell basically is a precursor to perovskite solar cell. A dye sensitized solar cell composes three main components. First component is a mesoporous N-type titanium oxide, and it is sensitized with a light absorbing dye, which is in the deck here. And then it is filled in with a redox active electrolyte. For instance, it could be electrolyte consisting of iodine, iodide ion. Now, generally, we require a porous nanostructured titanium oxide in this scaffold to maximize the surface area so that one can put maximum amount of dye on it to maximize the light absorption. And as a result, this stack is nearly 10 micron thick or so. And another downside of this structure is that it uses liquid electrolyte, which is a problem in terms of sealing of these devices. Now, the next invention in DSST came in the form of solid-state dye-sensitized solar cells, where liquid electrolyte was replaced by this wood transporting material spirometad, and because of limitations of
교수님께서 개설하신 거 아니야, 저희 그러면 시간적으로 아무런 영향도 없습니다. 그래서 그럼 내가 그 공유를 누르면 되는 거지. 이 방에서 만약에 공유가 열려 있으면 공유.
Can I request everybody to turn their microphone off?
내가 쓸게요. 네, 알겠습니다. 발표 볼게요. 네.
Hello. Please turn off all the mics.
Okay. So the next development came in the form of solid-state dye-sensitized solar cells, where one started using whole transporting solid-state material spirometad that stored as a whole transporting material. As a consequence of making the solar cell, the thickness went down to 1.8 microns or so, and this results in somewhat inefficient light absorption because of limitations of amount of dye that you can put inside the cell. And the next invention along this line was in the form of ETA cell, which was even thinner. In ETA cell, what one does is you again use one uses a TiO2 scaffold, which is nanostructured. And here, instead of a dye, we use an extremely thin absorber, which could be quantum dot kind of structure. And this is a very promising structure, which again can lead to very efficient light absorption. And the thickness of these devices is around 2 microns or so. Now, these perovskite structures are based on these kind of designs, especially solid-state dye-sensitized cells and ETA cells. Now, here, instead of TiO2, the initial designs used Al2O3. Al2O3 is an insulating material, it's a very stable material. And on the surface of this Al2O3, one coats this perovskite layer. And this is embedded or impregnated in a HTM, which was again spirometad or some other material. One can maintain a thickness of lower than 0.5 micron in this stack, and using such designs in the early stages of perovskite development, Miyasaka's group, they obtained efficiencies of 3.8%, where they deposited perovskite material on this TiO2 surface, and this perovskite were basically used as a sensitizer, and the electrolyte which was used in this case was liquid electrolyte. This efficiency was bettered by another group in Korea to efficiency of 6.5% with a rather stable PST device. The disadvantage with Miyasaka's devices were that they could last only for a few minutes. And improvement came in 2011 when a different electrolyte was used and efficiency was about 6.5%, and this led to a lifetime of 10 minutes. 10 minutes is not very good as compared to silicon solar cells, but of course, it was a major achievement for the perovskite solar cells. Major landmark in this area came in 2012 when durable 10.9% perovskite solar cells were reported, and here the perovskite was reported to be stable when it was in contact with a solid-state whole transporting material, namely spirometad. And this structure did not require, notably, the mesoporous TiO2 layer to transport the electrons as against the conventional wisdom at that point. And in about 2012, at the same time, people reported solid-state perovskite cell with efficiency of about 9%, and more importantly, the stability of up to about 500 hours. And the understanding at this point that emerged that perovskite itself is capable of transporting both electrons and holes. It's an ambipolar material. It doesn't need any, you don't actually require an N-type transporting material such as TiO2, so no mesoporous scaffold is really needed to make a good quality device. And remarkably, the efficiency have reached over 25% in 2019. So within a span of 10 years, perovskites have made significant journey from 3.8% to 25.2%. And that is what makes them a very exciting technology for the future. So right now, currently, the perovskite architectures that we use, we have moved on from the sensitized perovskite architecture, which used mesoporous TiO2 and perovskite mixture, which was in contact with P and N-type contact. So here, what happens is basically light is absorbed in perovskite, and it was earlier thought that electrons will conduct through that N-type TiO2, whereas the holes will conduct through the P-type phase. However, later it was realized that it's no longer necessary. So what one can do is that one can sandwich a thin layer of perovskite about half a micron thick between a P-type and N-type contact, and perovskite allows the formation of exciton, formation of free carriers, electrons and holes, and transport of these carriers to the respective electrodes in the same phase. And this is a structure which is a very successful structure. The typical perovskite material that was used in early stages, especially, and even now a lot of people use it, especially mixed halides, is this methyl ammonium lead iodide. And this iodine can be replaced by bromine and chlorine. And depending upon how you tune the composition, the optical band gap of these materials can vary from 1.5 electron volt to 2.3 electron volt. This is slightly higher than ideal band gap of 1.4 electron volt, but nevertheless, they are quite close. So how does a perovskite solar cell work? Well, you have absorber layer of perovskites, and you create electron-hole pair. The electron-hole pairs get separated because of a low binding energy, and these are then transported to respective hole and electron transporting layers. So this is an important configuration. You have to choose your hole and electron transporting materials quite appropriately so that their HOMO and LUMO levels are appropriately aligned with respect to HOMO and LUMO level of absorber layer. So you would like to transport the electron through the only electrons through the electron transport layer and only holes through the hole transport layer. And these are then carried to respective electrodes on both sides. So on one electrode you collect the electrons, on the other electrode you collect the holes. And again, the work function of electrodes have to be in such a manner so that they are appropriately aligned with the HOMO and LUMO of ETL and HTL. And so there are two configurations that we use in perovskite world. First configuration is PIN, second NIP configuration, depending upon the glass. So generally these devices are made on glass substrate. So glass is this coated with the FTO or ITO, the conducting electrode with high transparency. And if you put an N-type layer in contact with the FTO or ITO, which is typically TiO2 or tin oxide kind of material, then electrons are transported to FTO, and this is in then contact with the perovskite layer, which is the intrinsic material, and then you put a P-type layer on top, which could be a nickel oxide or P3HT or Spiro or another P-type material, followed by the metal. So this is a NIP structure. PIN structure would be converse of this. So instead of putting TiO2 at the bottom, you are putting nickel oxide at the bottom, for instance, and the top as an N-type layer, one can put PCBM or some other kind of N-type material. So there are a variety of material choices that are available to us. For ETLs, generally we can use TiO2, tin oxide, zinc oxide, or PCBM. And for HTL, one can use nickel oxide or moly oxide or Spiro or METAT, which is a conventionally used material, but it's expensive material, processing is difficult. That is why people are working to get rid of it. And then one can also use PEDOT, and PHT. So these are some material choices available. The important thing is one must choose ETL, HTL, and electrodes in such a fashion so that their energy levels are appropriately aligned to facilitate a flow of electrons to one side and flow of holes to another side without leading to both the carriers flowing in both directions. That will lead to loss of performance. So what is a perovskite structure material? Well, it's a AbO3 structured material based on the parent compound calcium titanate. And so this is the calcium titrant lattice. In the ideal form, it's a cubic lattice where A atom occupies the corner of the unit cell, the B atom occupies the center of the unit cell, and oxygens occupy the phase centers. And an important criteria for the formability of perovskite is its tolerance factor, which is sum of the radiuses of A and X ions divided by square root into sum of the radiuses of P and X ions. Generally, for alkali metal halide perovskites, the formability is predicted when T is between 0.813 to 1.107. So there could be off cubic distortions, which are very common in the perovskite world. So how do you view CH3, a solar cell kind of perovskite material in this context? Where here in this case, the A ion is methyl ammonium, CH3NH3. The B ion is the lead ion, which is a big ion, and X is, it could be iodine or bromine or chlorine, depending upon the composition that you have. And this is the kind of the atomic structure that would look like. A atom can further be replaced to tune the band gap and other optical properties by either formamidinium, which is CH5NH2, or even by cesium and rubidium. Compositional tuning, one can change the optical and electronic properties of this material. So there are many positive attributes of perovskite solar cells. I mean, they have high absorption coefficient, they have high carrier diffusion length, they can be made by solution processing, which is very good in terms of lowering the cost. They have tunable band gap by the means of weighing the composition. They have high carrier mobilities. They can be synthesized, the components can be synthesized at temperatures, and then they mostly consist of elements which are earth-dependent elements. So these are some positive attributes of perovskite solar cells. So this is, for instance, one slide that shows if you change the ratio of iodine to bromine, the band gap changes from about 1.5 electron volt to nearly 2.2 electron volt, and this shows the tunability of band gap. So it's possible, and this is also reflected in the color of the devices. And one can also change the absorbance accordingly. So this compositional tunability is a very strong aspect of perovskite solar cells, and this is where materials designers play a very important role, especially the chemists. Fabrication is very easy. There are two steps that we follow to make perovskite solar cells. One could use one-step solution deposition where you dissolve the organic and inorganic components in solvent, and then you spin coat them together, followed by annealing to form the perovskite phase in a single step. One can also follow a two-step solution deposition process where one first dissolves an inorganic component and then spin coats it, and followed by thermal annealing, and then again you can directly deposit this other component, that is AX, in a solvent, and then anneal it together to form the perovskite phase. Generally, it has been followed. The two-step solution deposition leads to better film quality. However, both the processes have given rise to good quality films. So there are many issues, however, with perovskite solar cell. The first and foremost is the presence of lead, which is an environmental hazard. And as a result, because there are many embargoes worldwide over the use of lead, and hence, and this is a very strong deterrent for the use of perovskite solar cells in commercial world. Another important factor which prevents their commercialization is poor lifetimes. They are affected by moisture. They have intrinsic stability issues. They also are affected by light, and they also tend to be heated under applied voltage. And there are devices which are not very mechanically stable as well. Another important problem that people see in perovskite solar cell routinely is the hysteresis, which means there's a difference in forward and reverse sweep of IV characteristics. And this is generally attributed to the migration of ionic charges as well as recombination. And then one major problem which often goes unreported in perovskite literature is device reliability. The device-to-device variations are massive, and process replication from lab to lab is a major problem. So we have seen that again and again. If you try to replicate a recipe which is shown in a paper in a journal, and often it is not replicable. So this is a major problem that we see in perovskite worldwide. So this is where we are going to hit upon is perovskite instability. It undergoes degradation under stresses, environmental stresses like humidity, light, heat, and oxygen. People have conducted some studies, not in great details, but limited studies suggest a few mechanisms. For example, under humidity, the methyl ammonium lead iodide decomposes into lead iodide and methyl ammonium iodide. And this methyl ammonium iodide further decomposes into methylamine and hydroiodic acid. And this hydroiodic acid further reacts with oxygen to form iodine and water, and the water again starts a degradation of perovskite. So it's a perpetual process that goes on. Under elimination also, the methyl ammonium lead iodide undergoes into formation of lead iodide and methylamine as well as hydroiodic acid. So these are some of the mechanisms which are acceptable in the literature, suggesting the degradation pathways of perovskite. And the job of device engineer is to slow down so you cannot completely stop the degradation, but what you got to do is to slow down the kinetics of these degradation mechanisms to prolong the device life. So there are various means to achieve this in a perovskite layer. For instance, one can achieve high performance perovskite solar cells with higher stability using doping at the cation site, which not only leads to tuning of optical properties but also higher stability. One can also conduct the doping at the metal site, which is a lead site, and this importantly results in lower toxicity, but it also results in tuning of optical properties. It doesn't seem to have so much effect on the stability. One important aspect that is conducted to carry out to improve the lifetimes is doping at the halogen site by either chlorine or many other ions, and they not only change the optical and electrical properties but also lead to better stability. And this is the focus of our study that I'm going to present in the next few slides now. So at IIT Kanpur, our lab basically stresses on few things. Our lab stresses on improving the lifetimes of perovskite solar cells. We also work on improving the process by use of benign solvents and to use low temperature processing protocols to reduce the thermal budget of device processing to really make the technology attractive. We also are working on to utilize lead-free materials, which is a topic for another talk, maybe some other time. And then we have also started working on developing tandem cells using perovskites, and in this we are probably going to collaborate with IIT Delhi as well with Professor Vamsi's group. So in this work, I'm going to show you some results that we have obtained by additive engineering by using PCBM, PC70BM, and ammonium chloride. These two compounds were added to planar, mind you, planar, not the mesoporous, compact perovskite solar cells. And the idea here was to analyze the effect of the grain size and structure evolution in the devices, and then to understand the effect on the device performance. We also wanted to examine the effect on thermal and moisture stability. And the clue to this came from our earlier work where we used PCBM as an interlayer in perovskite solar cells. That work is published in Solar Energy Material Solar Cells. And that shows that PCBM has a passive acting effect, and this leads to better performance as well as by the virtue of lower recombination in the devices. This is the device architecture that we have used. The methyl ammonium lead iodide is modified with the NH4Cl and PC70BM. We have stuck to MAPI because of it being a workhorse material, and one can easily compare the data with the literature. So I didn't want to go through complete process protocol, but what we have used is we have basically added NH4Cl to perovskite solution, which was prepared by mixing in DMF solvent, by mixing MAI and lead acetate, and PCBM was dissolved in chlorobenzene, which was later added to the perovskite solution to make a composite solution or modified solution depending upon the ratios wanted. So if you look at the effect on crystallinity, what we see is that if you compare with only NH4Cl, what we see is that there's a strong effect on the intensity of 110 and 220 peaks, suggesting that crystallinity and texture in these devices in the films with NH4Cl is far better. And in contrast, if you compare with the data with only PCBM doesn't seem to show that much improvement. So basically what we think is that the improvement in the crystallinity and the texturing is primarily because of NH4Cl. And this is also evident in if you just blow out or zoom out the 110 peak of films containing modified films and the unmodified films. There's a strong increase in the intensity of 110 peak. So that suggests 110 is texturing these thin films, which is beneficial from the perspective of perovskite solar cells. Another important thing that we notice is there is a right shift in the peak position, and this right shift in the peak position is indicative of changes in lattice parameter. So basically, because of smaller size of chlorine than iodine, there is a lattice contraction, and once the lattice contracts, the propensity of the material to form the defects reduces, and this, as we will see later on, reflects in better properties of the thin films of the devices made using these thin films. So if you look at the combined structure, combined effect on the structure, as you go from PC0, NH0, the control sample with increasing amount of NH4Cl to the bottom, the magenta one, we see substantial increase in the intensity of 110 peak, which is basically signature of increasing 110 texture in the devices. And this is all another important repercussion of this is the change in the grain size. So if you look at the FASM micrographs, on the left we have the FASM micrograph of unmodified films, which shows a very fine grain size of less than about 100 nanometers. And if you add only PCBM, the grain size doesn't change, the grain size remains similar. However, when you add only 10 milligram of NH4Cl to the perovskite solution, don't worry about the 10 milligram, it's in the 8% in the end. So, so 0.15 molar, in fact, you can say, the grain size of these materials changes to more than a micron. And if you look at the sequential variation as the NH4Cl content varies, the grain size changes from about 600 nanometers to 1200 nanometers to nearly 2 microns. So there's a significant increase in the grain size, and this is very important because grain boundaries are pathways for degradation as well as defects and moisture diffusion in perovskite solar cells. So if you can control the grain size, you can control their properties. So what we see here is there is no effect of PCBM on the grain size, and grain size significantly increases with NH4 addition. We also noted the presence of chlorine in the films through EPMA, electron probe microanalysis, which suggested the presence in both grains as well as grain boundaries. And this seems to suggest that presence of chlorine in the material could alter the nucleation and growth kinetics, resulting in the observed change in the grain size. So, however, at higher chlorine concentrations, what we observe is that at the triple junctions of grain boundaries, one can observe some porosity. So you can see some pores coming up at the triple junctions, which is also reflected in deteriorating performance of these devices at higher concentrations. And this is also reflected in higher roughness of the devices. So as you increase the NH4Cl concentration, the roughness changes from nearly 10 nanometer to about 40 nanometers at highest concentration. And this could result in improved contact with the top layer. So this is the nucleation growth kinetics model that we propose, that in the perovskite film without NH4Cl and PCBM, you have one has higher nucleation and lower growth rates, and this results in a smaller size of the grains and also decreased 110 texture. So this vector is basically HKL, which could be 110 vector. So 110 direction is randomly oriented or more randomly oriented, but when you look at the perovskite with NH4Cl and PCBM, lesser nucleation rate or higher growth rates results in bigger grains and enhanced 110 texture. And as you know, that the size is proportional to I over G to the power minus 1 by 4. As you decrease the nucleation rate, R increases. As you decrease the growth rate, the R increases. Both favorably for devices. Can I request one of the participants to turn the mic off?
Ashish, I wanted to remind you, time is running out.
Yes, sir. Yes. I'll just take 4 more minutes. And if you look at the PL spectra of these devices, upon addition of NH4Cl, what we see is that there's significant PL quenching in the devices. Not only there is a PL quenching, but also there is a blue shift, which suggests that the charge direction could be better, and also the trap passivation that takes place could end up making the devices better. So if you look at the photovoltaic performance of these devices, the devices which contain NH4Cl and PCBM, they show very good JV characteristics, especially at the 10 NH4Cl devices, which show champion efficiency of about 17%. 17% is not a good number in terms of 25% highest, but it is a very good number in terms of compact devices made on MAPI. So we have to compare the apples to apples. In the context of MAPI, it's a very good number. And moreover, the difference in forward and reverse characteristics is not very significant. So if you look at this table, we work out the hysteresis index. The hysteresis index, which is the difference between reverse and forward characteristics. The hysteresis index is minimum for the devices containing 10 milligram of NH4Cl, whereas other devices have higher hysteresis index. So these devices show higher efficiencies, higher fill factor, higher VOC, higher current, and lower hysteresis index. suggesting that grain size improvement and PCBM addition have strong impact on the performance. And they also result in better reliability. There is lower scatter in the performance of NH4Cl containing devices. Also, the EQ of these devices is better as compared to the control devices. And there is also a blue shift in the EQE data due to chlorine incorporation. So if you look at the environmental and stability studies, we conducted environmental stability studies of control and modified sample. What we see is that at a humidity of 50 to 60%, temperature of 25-30 degrees centigrade, we can retain 85% efficiency of up to 100 days, which is we have not tested up after 100 days. Many tests are still undergoing, but this is a remarkable improvement in the performance of perovskite solar cells. And what we believe is that this is happening because of decrease in the grain interfacial area, because of increase in grain size, and also attachment of PCBM to the halogen atoms at the grain boundaries, resulting in reduced water ingress because of reduced grain boundaries and making the devices more moisture resistant. The thermal stability studies are also very remarkable. We can retain 80% efficiency up to 500 hours. And whereas control samples are degraded within less than 100 hours. Humidity was kept lower for these studies to primarily look at the effect of temperature. And this is basically reflected in the slow kinetics of degradation. The devices containing, in the control devices, the PBI2 creation is very fast. So you can see the PBI2 peak is extremely quickly formed, whereas in these devices, the PBI2 peaks are of lower intensity. And one can see the perovskite peak of quite significant intensity even after 500 hours. So basically, this is because of slower rate of deterioration of perovskite into PBI2. And this is again because of larger grain size and presence of PCBM, resulting in slower kinetics of PBI2 formation, suppression of deep traps at the grain boundaries, and larger grains, which means there are fewer moisture permeation pathways, which could be significant at higher temperatures. And as a result, we obtain improved thermal stability. This is also attributed to the formation of chloride phase. The thermal analysis shows that device containing NH4Cl shows slowest degradation kinetics. As you can see, the kinks which are appearing shift progressively to the right at higher temperatures. So especially under 200 degrees centigrade, these devices are more stable. That is why these materials are more stable as compared to pristine materials. So these are the takeaways from the talk. The addition of materials like NH4Cl and PCBM, which have a dual role to play. The NH4Cl leads to increase in the grain size and crystallinity and texture. PCBM leads to improved passivation. Together, they lead to decreased defect density and lesser recombination, leading to more than 110% increase in the power conversion efficiency and lower hysteresis. And what we obtain is excellent atmospheric and thermal stability, as we just saw. And the contributing factors are basically improved bond energy, resulting in lower defect formation energy, and also resulting in lattice contraction and grain boundary passivation and reduced defect densities. We are studying this further to improve our understanding of what are the microscopic reasons behind its improved stability and performance, but overall it looks very exciting. And we believe that similar approaches can be taken forward, especially for mixed cation or mixed type. With this, I'll stop here. If you have any questions, I'll be happy to answer. Thank you very much. Professor Kumar, I'm having a lot of noise from your side.
Is it better now? So there are some talks. I don't see any questions, but to begin with, I can ask just a small question. I think I may have missed, but you did not mention the area of your devices, what you are using for all the stability studies.
Okay, so these devices were made on pixel size from 3 millimeter by 3 millimeter to 10 millimeter by 10 millimeter. So we have varied the area from 9 millimeter square to 100 millimeter square. So of course,
so all this
stability of both the areas remains same, but efficiency goes down as you increase the size. So that top efficiency goes down.
Yeah. Yes, yes. Okay, so you have not attempted to increase the area yet, but
No.
it's
As
concentrated.
I said, that we have increased the area from 9 millimeters square to 100 millimeters square. We have already done that.
Yes, yes, that is okay, but not so.
Not
Okay.
beyond that. We are in the process
Yeah.
of making modules, mini modules.
No, no, I think it's important to address the issue of pretty much more than the area.
Absolutely, absolutely.
Okay. Another thing I wanted to ask, if there are no other questions from the audience, is you said lead-free perovskite, but how important is lead-free perovskite? Because how much is lead is there per watt? If you assume a, let's say 20% efficient cell of perovskite and also silicon, then silicon cells also have lead in joints and all that. So
Yes.
My feeling is that the amount of lead you have per watt is so small that it is not worth by trying to remove the lead from to go to a lead-free cell site.
This remains a contentious question. There are proponents, opponents of use of lead in perovskite solar cells. So proponents suggest that yes, there is lead in silicon solar cells, there is cadmium in cadmium telluride solar cells. So what is the problem in having bit of lead in the perovskite solar cells? But at the same time, people in US and Europe, they say that Europe and America are having very strong embargo on the use of any amount of lead in the devices. Eventually, even the lead that is used in silicon solar cells is going to go away. So that is what they are proposing. But these are two schools of thoughts. So there is no clear-cut consensus. But I agree with you. I mean, the amount of lead which is present is the only problem that is there is these materials can degrade in the presence of humidity. So the amount of lead that can leach out could be significant. Whereas the lead in the silicon solar cell doesn't leach out. So if we can prevent the leaching of lead from these materials, that could be good.
Okay. Okay, I think there are no question. One question came on chat box. P.PSS has been used as a flexible electrode in case of solar cell. It is used as an HTL. Is it acting as an electrode as well as a HTL, or a different layer of metal electrode is required for solar cell? The question is from Ms. Bushara Fatma.
Okay, so P.PSS is used both as HTL as well as electrode, but you have to use different formulations of P. To make it work as both. Generally, in solar cells, it is used as a cold transporting material. But the problem with P.PSS has traditionally been its susceptibility to moisture-assisted degradation. And that is why it has not found enough traction in the solar cell literature based on perovskite especially.
Okay, thank you, Professor Garg.
Thank you, Professor.
For your talk. Very excellent talk. Good work.
Thank you, sir.
Thank you. So now we go to the next invited talk by Professor Jong Hong Jung. I hope correctly. Professor Jung is from Inha University in Korea, and he is a professor from PhD from Seoul National University, and interested in piezoelectric and pyroelectric and triboelectric nanogenerators. So he's going to talk about triboelectric nanogenerators for mechanical energy harvesting from water droplets, etc. So thank you, Professor Jung. The stage is yours. Please.
Thank you, Chairman. Can you hear me?
Yes, please.
Yes, thank you. Hello, everyone. I am Professor Jong Hoon Jung from Inha University, Korea. Now in Korea, it's almost 3 p.m. So, and very cold, but I enjoy this talk. First of all, I would like to give my sincere thanks to organizer to invite me in this wonderful conference. My talk is I think most of you in this room may interested in the solar energy, but my talk is related with mechanical energy harvesting among various renewable energy. While the topic is a little bit different, please enjoy. In our daily life, there are lots of waste mechanical vibrations like blood flowing and heart beating, wind and wave. If the small device called the triple electron nanogenerator can convert the mechanical vibration into electricity, we can operate small device like MEMS and nano device without battery. The working principle of TNG is very simple. When two materials contact, the two surface has a positive and negative charge based on the triple electric series. When the two materials are separate, potential difference will be formed. So the pre-charge will flow along the load. So if the two materials are vibrate by the mechanical vibrations, the voltage will be formed in this way. So in this way, we can harvest the mechanical vibrations into the electricity by the TNG device. Among the various mechanical vibrations, our group are interested in the ocean. As you know, the ocean has a very huge mechanical energy. Its energy is very insensitive to weather, season, and location, but it is very difficult to access and very irregular, random, and directional change. To harvest the mechanical energy of the ocean, our group are interested in the floating buoy. As you know very well, the floating buoy is widely used in sea and ocean, especially in the coastal area. If we make a device based on the floating buoy, the device should be very cost effective and minimize the coverage of the sea and easily replaceable after long-term use. To make a device, we make a design very simply. This is a device illustration. The device consists of 3 parts. One is power generation unit and acrylic supporter and acrylic and buoy. In the power generation unit, we arrange at 45 degrees, and for the supporter, the height can be adjustable. When you see the power generation unit, the PTFE bar, polymer bar, will be oscillate inside of a PS polymer, and copper electrode are left in the outside of a PS. And this is a real photo of the device. When the PTFE bar oscillate inside the PS, the current will occur only when the PS bar is vibrating in between the two electrodes. And the such thing we confirmed by this console simulation. To increase the power generation efficiency, we perform the power surface modification using the argon plasma etching. As you see here, the roughness of PTFE sharply increased as we perform the etching, and the potential also sharply increased by the negatively. To understand the origin, we performed the XPS measurement, and we found the chemical species strongly modified from CC and the CF2 in PTFE to CC and the COX and the various CF. Especially, we think COX may dominant role for the lowering the potential. Yeah, this data shows the optimization of a power generation unit. We use the plasma etching to increase the roughness and surface potentials. And we use the interdigital electrode with the same length of the copper electrode and to increase the inertia to increase the contact event. All of them increase the power generation efficiency. Yeah, second, we optimize the output performance of the device by enhancing by increase the height of the power generation unit. The origin is, of course, due to the enhanced torque. And the other thing is we found that the obtained current is almost directional independent. This result is very important because as you know, the water wave can come all other directions. So it means our device can generate electricity for all weather and season and time. Second, we think of the random amplitude of frequency of the water wave. First, we consider two different amplitude of water wave and found the device that generates the current for each amplitude. And when the water wave has two different frequency, the device also generates current for each frequency. And then we think about the harsh environment condition of the ocean. As you know, the ocean is very salty, and the ultraviolet is very strong. But even such a case, our device generates a very stable current, as I shown here. Second, we consider the temperature, low temperature and high temperature of the ocean. Between the 4 to 6 degrees C, we found that the current density and the voltage is almost the same. And even for the hot temperature of 60 degrees C, the device are stable up to 74 hours. Yeah, to apply the protein buoy based device, first we this is a device and apply the wave, and then the LED can be brightly light up. So this is very important for the safety issue. And we found that after 1 hour charging and turn on the capacitor, then the thermal hygrometer are turned on. And we notice when we use just only one FETNG, it takes around 2 hours. But if we use the two device, the thermal hygrometer are turned on around 1 hour. It means if we use the array, it can reduce time, and then we can monitor the temperature and humidity in real time. I think the temperature and humidity and wind speed is very important for the weather monitoring. So let me summarize the first part of my talk. We easily fabricate the protein-based device with low cost, and the argon plasma treatment are very effective to increase the triple electrification. And the nano generator produce around 30 volt and 1.2 microampere for mild water waves. Yeah, second, we investigate the serious wear problem in the TNG. As you know, the working principle of TNG is just contact and separation. So if we continue, the surface will be damaged like this one. If the surface is damaged, the voltage is sharply decreased only around 100 seconds. It means that this kind of, because of the serious wear problem, we cannot use the device to harvest the water wave in ocean because it is the voltage is sharply decreased. To solve this problem, we use the ferroelectric materials, as I shown here. This is the conventional TNG device. For power generation, we need continuous contact. So after a very long time, the surface became very dirty, and there are lots of debris, and the power will be sharply decreased. On the other hand, when you use the ferroelectric polymer, like a PVDF, then only random contact is enough for power generation. Because of the random contact, the surface are very clean and sharp, and the power does not sharply decrease, but it's only slowly decrease as compared with the conventional TNG. Yeah, such thing can be happen because when we use the ferroelectric TNG, when it contact, lots of power will be generated, and this power will be decay as time goes on. Yeah, as time goes on, and when we make a non-contact, then the charge will be significantly increased because the charge still remained here. On the other hand, for the case of conventional TNG, when it contact, the power generation is very small, so it decay with time. And when we make a non-contact, only only minute charge can be generate. So that we cannot we cannot use this kind of thing. Yeah, such a thing is possible because the contact potential is different. Yeah, this view graph shows the contact potential between the ITO electrode and PDMS. And below the PDMS, we put the PVDF with the up polarization and non polarization and down polarization. As you can see clearly, the potential difference is very large for the case of up polarization, but the potential difference is very small for the non polarization. It means when we contact, the loss of charge can be transferred from the ITO to the PDMS for the up polarization case. But the non polarization case, only small charge can be transferred from the ITO to the PDMS. Yeah, to demonstrate the power generation during the non-contact, we simply shows the operation of LCD and LED. As you see these two movie, you can see that this ITO does not contact with the PDMS, but just approaching and receding. Even in this case, we can turn on the LCD and the LED because of the ferroelectric polymer. To increase the power generation efficiency, we make array stacked along the upper direction and apply the water wave, and it go up and down. And after 30 minutes, this will be charged, and this is the wireless sensor. And if we turn on, it start display the temperature outside. Note that we do not use the we use only the wireless connector, wireless. So it continue up to 20 minutes. So this data is obtained by the wirelessly obtained by the computer, and this is the temperature display in the high group thermometer, and this is almost consistent. So let me summarize the second part of my talk. We demonstrate the plausible solution for the wear problem of DNG, and we shows that the contactless power generation is possible when you use the electric dipole of the ferroelectric polymers. And we apply these things to the inaccessible area like ocean, underground, and underwater. Third, and last, our group are interested in the water droplet. As you know very well, the water droplet is everywhere, like the shower faucet and the rain, but it has a very tiny energy. So our group interested in the water breaker. As you see, and as you can imagine, in Ireland there are lots of water breaker. For example, this is a map of south part of Korea, and there are lots of island. So if we consider the island, I can easily imagine around 5,000 water breakers in south part of Korea. So even though the water droplet energy is very small, because of the large number of water breaker, the generated power will be greatly significant. To harvest the mechanical energy from the water droplet, we made the interdigital based device. This is the schematic diagram how to make an interdigital device. So we attach the aluminum for the PET polymer, and using the cutter we make an interdigital electrode, and put the PTFE. Please note that the aluminum does not directly contact with the water and the water droplet, so we can the electrode does not is very stable. Because of the PET polymer, the device is foldable and twistable and rollable. It means our device can be applied for various shape of a water breaker. Second, we investigate the role of interdigital electrode. So for the electrode, we first do not make a gap, and this we make just one gap and then many gaps. And water droplet are falling in this device, and found just one peak for this case, and 3 peaks for this case, and many peaks in this the interdigital electrode. Because of the many peaks, we can get the larger charge for the interdigital electrode as compared to 1 or 2 electrode case. Second, we consider the droplet size and the speed. As you can see, if the electrode width is around 20 millimeter, the largest charge occurs when the droplet size is very close to the electrode width, like the 19 millimeter. And when the droplet size is fixed, and we observe the charge, triple charge increased as the increase of the speed. Yeah, second, we make the cone-shaped device. The green line is inter electrode, and because of the cone shape, we can change the theta of this angle. And if the theta is large amount of water droplet can be get, but the speed is slow. If the theta is small, then the only small part of water droplet will be generate, but the speed is very large. So that we consider theta dependence and found that when the theta is larger, the average current is became large. And of course, the signal is also depend on the water volume. Yeah, and last we we made a cylinder type device, and this is the interdigital electrode, and in the interdigital electrode we put the water and shake, and we got around 220 volt and 400 nanometer current, and the power is enough to turn on the several LED as is shown in this movie. Yeah, so I want to summarize the third part of my talk. We observed the sharp increase of triple electric current in interdigital electrode-based triple electric nanogenerators, and we showed that reliable and durable device structure for various kinds of water droplet and diverse sprays. And the maximum triple electric charge for similar width of droplet size and droplet width, electrode width. Thank you for your attention.
Thank you, Dr. Young. Very interesting talk. Let us see if there are any. Yes, there is a question, I think something in chat box. One question somebody asked of the metal electrode and the performance of tank. If we change copper electrode by aluminum electrode or vice versa, will there be any change in the output performance of tank?
Yeah, because I used only copper because it's very cheap. But no matter what, if we use the aluminum, almost the same.
Mr. Kumar, can I ask a question?
Yes.
So I had a question on whether you showed about the non-polarization in one of your slides.
Yeah.
Up polarization, non-polarization, and down polarization.
Yes.
So why do you say that ITO PDMS is a
non-polarization?
Given that there is a potential difference of about 2 to 3 volt?
Because the contact occur between the ITO and the PDMS, okay? And the PVDF has a polarization and down polarization and non-polarization. Because of the if for the case of polarization, the interface between the PDMS and the PVDF has a plus charge. Because of the plus charge, the potential will be increased.
Okay, I'm not sure I got it.
Okay for you?
Professor Vikram Kumar, can I ask a question?
Sure, please.
Professor Jung, this is Neeraj Khare.
Yeah.
So actually, this point is not very clear from your talk, how the use of ferroelectric material can solve the wear problem.
Mm-hmm. Okay. So I think if you see this data, I think you can understand.
Yes.
Yeah, there are two TENG. One is this is a conventional TENG, and this is a ferroelectric TENG. Okay, and as I show you, because of the modulation of surface potential, when it contact, the ferroelectric TENG generate a very high power, but the CTNG just small power. But this discharge will be decay with time. Okay, but because of the high power, even though time goes on, the large considerable amount of charge is still there. So if we just moving the IT electrode to the polymer without contact, it shows the considerable signal. But if for the case of conventional TNG, because the power generation is very small, if the time goes on, this is almost zero. So even though the ITO are very close, it does not occur the power generation. Yeah, this is the key idea.
Okay, all right, thanks. And for your this water droplet device that you showed used in the sea wave thing, so is there some capacitor or something attached with it for storing power, or it is just generating power and using it somewhere?
Because in this case, we just use the operator LED, so we do not
Okay.
use the capacitor.
Okay, all right.
Yeah.
Thank you. Thank you, then. Nice talking. Thanks.
Okay. Okay, Dr. Professor Young, there's a question on the talks from Ms. Bushara Fatma.
Check.
Yeah.
Yes.
Devices. Other devices like is it a are you okay? Do you understand the question?
Yeah, I think. No. Basically, we the connect by the parallel connection. Most of the array we use the parallel connections. Are you okay?
Yeah, I think this has answered the question because he's asking whether parallel or series connection. Whether it runs
We use
parallel.
the parallel connection.
What about yeah. Okay. Okay. Okay, so I thank Dr. Young for a very interesting talk, very good talk, and especially this with the rain droplets. If we can use droplets, it will go a long way to generate power. Thank you for the very good talk. Now I have to invite some oral talks are there. Oral running 5 minutes late. Dr. Ashok Sharma, are you there?
Yes, sir, I am there.
Okay, so now the next talk is by Dr. Ashok Kumar Sharma, who is working at NCPRE in IIT Bombay. So let's please go ahead,
Thank
Dr.
you, sir.
Sharma.
Thank you, sir. I will start. As my screen is visible to everyone?
Not yet, not yet.
Connectivity.
Once again, you unshare Dr. Sharma, so that, and then again share it. We can see now. Put in the
Okay. May I start?
yes.
Yeah, thank you. Good afternoon to everyone. I'm Ashok Kumar Sharma. I'm a senior scientist at National Center for Photovoltaic Research and Education at IIT Bombay. And I thank the organizer to giving me this opportunity to share some of the work which is relevant to the current mass production technology, that is PERC. And we have explored some things over there. So I'm going to share in next 10 to 15 minutes our observation. So the title is basically the troubleshooting the efficiency variation in PERC silicon solar cell pilot production line using advanced imaging characterization techniques. So basically the background of this work comes from that NCPRE is very much involved in the providing service to the Indian PV industry and some of the industry abroad. So we got this opportunity, one of our industrial user, to troubleshoot their pilot line in terms of understanding what are the problems they found in the efficiency variation in the different pilot lines actually. So the back outline of my talk is basically first I will a little bit explain about the PERC silicon solar cell technology and its scope and future, world market share, and thereafter some of the processing challenges, the general challenges usually most of the pilot lines having. And in the section of the scope of the study, I will explain that how we have chosen the cells for the characterization and what are the tools that we have used in order to characterize the cells. And thereafter, obviously, there is a result and discussion which is enriched with some of the conventional measurement of solar cell performance like JV measurement, and thereafter fill factor analysis, and further we go into in order to investigate the mapping things like series resistance mapping. So overall it's a recombination and resistive losses what are happening there in the chosen cells, and thereafter I summarize my observation. So as we move from the PERC silicon solar cell technology, that we all are very well aware that the passivated emitter and rear contact structures are the most promising technologies currently in the mass production, and the efficiency range is obviously that it is varying from one place to other place due to many reasons. So that's why the range is provided over here. So if we see the conventional technology, aluminum BSF, which is since very long time, it is the workhorse of the PV arena. However, these PERC structures are coming in the quest of the making the high efficiency solar cells, and in order to do that, the scientists and the researchers found that reducing the rear surface recombination, which is generally in case of aluminum BSF is very much high, and some of the surface reflectivity and other issues that result some of the difficulties people found in maintaining the fill factor, and that we also found at our place as well. So this particular work is also about the how one can put an equilibrium between all these factors so that we can increase the efficiency. So here the major concern is when we are applying a rear application, which is similar to the front in park, has to be laser ablated, and its geometry etc. will also affect the solar cell performance. So this area is very much concerned one, and it has to be taken very much care when we are fabricating park solar cells. So let's have a look about the world market share and future projection. So this is the picture taken from ITRPV report 2020, and here we can see, apart from other high efficiency technologies, the PERC share is enhancing rapidly. As we can see, in the year of 2019, it is taking around 65% of the total market, and it is also well projected that it is the technology associated with some of the other one that it will stay as a PV workhorse in the coming decade. Now coming to the processing challenges. So as we move from a lab to the mass production, obviously the large area things come into the play, and that creates the various issues, like very general issues. Those are the non-uniformity issues. So let's look in the aspect of the PERC solar cells. So their back surface is a key reason where the most of the things that we are actually gaining from the aluminum BSF that we are not having in aluminum BSF, which is coming from there. So again, this is a quite sensitive area in terms of producing the high efficiency, generating the high efficiency from PERC solar cell. So this is the listed some of the latest development people did in the area of PERC solar cell is the back surface polishing. It means the preconditioning of prior to the passivation layer coating and its thickness etc. And people also tried the lot of stacks in there, and the capping of silicon nitride is also one of the important aspect over here. And thereafter, this is not only the passivation, when we are putting aluminum coating, aluminum paste over there, printing, basically the opening of that dielectric is very important aspect. And we also did a study, soon we are going to publish this in some of the journal, that the circular laser ablation is rather good enough in order to contain the recombination due to metal assisted rather than the linear ablation. So in case of pilot production, process uniformity is a very big concern, and here we also can see in my talk that how it is affecting the cell efficiencies and performances. So in the scope of the our study, actually in their these people have contacted us and they said we have 3 pilot lines, and we are finding that there is a variation in the efficiency. However, we are using same type of processing etc. So in that case, what may be the reasons behind that? So we actually requested them that please give us some sort of cells, and we have taken all those cells and we investigated what may be the cause of the efficiency variation in their production lines. So here I am going to present the result from only 3 cells, which is taken from 3 different bins, and it is a common business in the production lines that the bins are the moderate efficiency, high efficiency, and the lowest efficiency people used to take. So we have taken 3 cells from 3 different bins associated with their efficiency, and thereafter we utilize the mapping techniques apart from conventional one like ALBIC, photoluminescence, under biasing, and under open circuit, and generate the resistive and recombination losses maps. And we also found that our analysis is also approachable for the other high efficiency and high generation silicon based solar cells as well. So let's move on the result and discussion part. So this table, it is shown over here, the 3 cells A, B, and C, there is a huge efficiency variation which we may be taken as a average efficiency of those bins. So cell A is showing the very high efficiency and cell C is showing the lowest efficiency, and the major role playing factor is the VOC and fill factor that we found from the IV characteristics. Now it gives us an insight that we have to look into the matter of the fact that why the fill factor is changing in all these cells as well as VOC. So then we did the fill factor analysis, and this is one of the very good approach. I can appreciate the efforts of Dr. Khanna from SARIS Solar Energy Research Institute of Singapore. They come up with this approach where only the IV characteristic data is helping in order to get the the losses in the fill factor by means of the shunt series J02, J01, etc. in percentage manner. So we also utilized their work, and we found that in this one that cell A to C, when we are moving from cell A to C, that the loss in series resistance and J02, which is actually associated with the recombination in the space charge region, and the the causes very much difference over there when we comparing with the cell A, and it found that these are the two factors which are playing very important role. Then we further investigate and utilize our mapping techniques in order to what is happening over there. So we did the this biased photoluminescence imaging approach, and we found that that cell A display overall lower RS across the solar cell surface area, and fortunately it is also come very close to the numbers that we found from the IV characteristic calculation. And here we can see, if we go to cell B and C,
Sure,
then there is a
please.
sorry.
Time is
Okay,
already coming out.
okay, sir. Okay, sir. So we found that the series resistance is higher in case of C and B, and it is mainly coming from the peripheral region, which is quite observable in this image in here as well as in C, for cell C, actually. Then we the PL imaging under the open circuit, and we found that the identical features are also observed under the open circuit condition. And we know that the open circuit condition photoluminescence imaging is basically the image of the carrier lifetime, local carrier lifetime. So ultimately it is quite related to the passivation at the higher side, because the other images taken were not affecting in terms of the passivation, etc. So we found that the similar identical features were available here as well. Then we, in order to further investigate and further verified our facts, we did the back surface recombination mapping, which is we found that higher range, and then created the surface recombination mapping that is also identical to the observation from the peer imaging and open circuit as well as the series resistance mapping. So we can say that the non-uniform back junction removal, which is the important aspect or processing is taken into account when the processing happening, it seems to be probable reason that affect the passivation and contact formation at the rear end. So now I would like to summarize my observation that in this work we have comprehensively utilized the combination of photoluminescence imaging and light beam induced current for evaluating the performance of the cells. And we found that the region of process ambiguity, which is leads to cell efficiency variations, are the mainly the edges area, which is accounted for this troubleshooting actually. And presently we engage in the exploring the DLIT. This is the lock-in thermography technique that recently we have established at our place to generate the mapping of the parameters like shunt resistance, J01 and J02, in order to verify our facts in terms of the imaging of the solar cells. So this is the I summarize my talk over here. Would like to acknowledge the MNRE for funding the NCPRE and giving the opportunity for the young people like me for exploring the PV arena. We also thank to MSPVL for providing PERC silicon solar cells and utilizing the techniques and the work we have developed at NCPRE. Thank you very much.
Thank you, Dr. Sharma, for a very interesting talk. We are running out of time. If there are any question in the chat box, there is one question. We have observed that it takes time to achieve saturation, the voltage in current output. What was the saturation? I think this must be referring to the previous speaker.
No, sir, I ask one question.
Please ask.
Dr. Sharma, so what is the overall I would like to understand the fill factor analysis. So you want to open that it is not only represents the series and shunt, I mean like a recombination also. The fill factor also can explain the recombination in the space charge region.
Yeah, you are true. Yeah, this is the fact that we found that it is fill factor is not only losses, it is also combining the recombination losses as well.
So that is the steady overall means like you are going to tell us that.
Yes.
Okay, thank you.
Thank
you. Okay, so we thank Dr. Ashok Sharma for a very interesting talk and a very powerful technique that you are using. So thank you. And now I invite the next speaker, Dr. Rudram Hemojit Singh from IIT Delhi. So he's going to talk about triboelectric nanogenerators based on zinc oxide, PVDF zinc oxide. So Dr. Singh, floor is yours.
Yes, sir. Is my slide
Please go ahead.
Visible, sir?
Yes.
Okay. A very good afternoon to all of you. My name is Hudram Hemojit Singh, and the title of my presentation is Role of the Polarization State on the Performance of PVDF zinc oxide based triboelectric nanogenerator. And this work has been carried out under the supervision of Professor Neeraj Khare. So here is the outline of my presentation. I will introduce about the triboelectric effect, triboelectric nanogenerators, the working mechanism of triboelectric nanogenerator, preparation of PVDF zinc oxide films. Then I will discuss its results and discussion section, then conclusions, and then acknowledgements. So first, there has been increasing number of electronic devices, mostly the mobile phones and the wearable electronic devices. Even though their size has been reduced and they are becoming more slimmer and slimmer, we have to squeeze the size of the batteries also. That is why we need to charge the batteries again and again. And as you see, although the power consumption of these electronic devices has been reduced drastically, but the number of these electronic devices is very huge. So there are lots of power required for charging these electronic devices. Right now, we have these solar cells and windmills where we can harvest the renewable energies very effectively. But the main problem is that they have to be stationed in a very large area. So we cannot use this kind of energy harvesters in mobile phones or wearable electronic devices effectively. So there is another kind of energy which has been going wasted if we do not harvest them. That is mechanical energy, and they get wasted in the form of sound, heat, and other mechanical energy. So we want to harvest this mechanical energy, and to harvest this mechanical energy, there are three main approaches that have been following. One is the piezoelectric effect, another is triboelectric effect, and the third one is the pyroelectric effect. But we have been working on this piezoelectric and triboelectric effect. But in today's my talk, I will be focusing on triboelectric effect only. So triboelectric effect is known to us since a long time. The best example is when we comb our hair with the when we comb our hair and when we put this comb over a small piece of papers, it will get started attracting. So the charges generated on this pump and this uh, glass rods are because of the triboelectric effect. So since in 2012, Professor Zhonglin Wang and his group started working how to extract or how to harvest electrical energy from this triboelectric effect. So Uh, it is basically a combination of this triboelectric effect and the electrostatic effect. So the charges are generated when rub or when we touch these two materials together, and these charges are generated on the uh, surface of the highly insulating materials. But when we separate it out, there is an electric field induced between these two materials, and this leads to the induced electric effect on the metal electrodes, which we put here on the back side of this highly insulating materials. So there are four possible different modes of triboelectric nanogenerator: contact separation mode, lateral sliding, freestanding, and the single electrode mode. The previous invited speaker has already talked about the lateral sliding mode, but in my talk I will focus on contact separation mode. So this is one of the animation where how the charges are electricity is being generated using a triboelectric effect. As I mentioned, it is a combination of triboelectric effect as well as electrostatic effect. So based on what kind of mechanical energies are available in this form, there are different designs like rotating type of triboelectric management, this sliding, and based on from where we want to harvest this mechanical energy. So we have, as I mentioned, that we have been working on this piezoelectric based nanogenerator. So polyvinylidene chloride PVD is a highly ferroelectric polymer, and it has different phases, alpha, beta, and gamma phases. Out of the three different phases, beta phase is of great importance because of this molecular arrangement, which leads to the uh, formation of electric dipoles. So we want to increase the beta phase content of PVDF so that it will be more useful as a ferroelectric polymer. And we are going to use zinc oxide, which is also having a non-centrosymmetric structure, which has inherent piezoelectric property. So we are going to make a uh, flexible nanocomposite film of PVDF and zinc oxide, and we are trying to see how the triboelectric property of PVDF can be enhanced. So for synthesis of zinc oxide, we use the hydrothermal method, and zinc sulfate and sodium hydroxide were used as precursor solution. And then we did this XRD and the TN analysis for the confirmation of the successful formation of the zinc oxide. And those zinc oxide nanorods were introduced into the PVDF matrix by introducing these zinc oxide nanorods in the well-dispersed PVDF solutions, which are dissolved in DMF. And after that, we drop phosphate the solution over the glass substrate, and we bright the film, and then we peel it off. After peeling off, we got a freestanding flexible film. So this is the XRD analysis of the zinc oxide PVDF nanocomposite film. We uh, confirm that from the XRD analysis, the beta phase has been enhanced, but in order to confirm the beta phase content, we did the FTI analysis. But in the FTI analysis, this X corresponds to beta and gamma phase also. So we have to deconvolute the curve so that we can identify how much beta phase and how much gamma phase is present. So we calculated and found to be 76.1% of beta phase content in the zinc oxide PVD film. So the reason of getting more beta phase in the PVDF is that when we introduce these nanofillers, that is zinc oxide nanorods, into the PVDF matrix, the surface charges of the zinc oxide interacts with the CH2 CF2 dipoles of the PVDF, and due to the interaction of the dipoles of PVDF with the zinc oxide nanorods, they are uh, forced to align in a particular direction, and that that alignment led to the increase in beta phase content of PVDF, and this has been confirmed from the FTI analysis. When we see the vibration modes of CH2 dipoles, the peak has been shifted towards the lower angle, because when there is an interaction between the CH2 dipoles and the zinc oxide nanorods, the effective mass of the CH2 dipole increases, which led to the decrease in the energy of vibration energy. That is why it is shifting in the lower numbers. So apart from the increase in beta phase, we found that the dielectric constant of PVDF also changes when we introduce the zinc oxide into it. And when we see the surface morphology, it becomes more kind of a rough surface when we introduce zinc oxide into it. And then we measure the contact angle in order to check the hydrophobicity of the film. And it is found to be increased. Hydrophobic nature of the film is found to be increased. So these properties play a very important role in the performance of the triboelectric nanogenerators, the dielectric constant, the surface roughness, and this hydrophobicity. So we did the polarization electric field measurement, so it's found to be increase in the polarizability of the zinc oxide PVD film. Then we also did a PFM measurement because we wanted to know the piezoelectric coefficient of the zinc oxide PVD film. It's found to be 70.3 picometer per voltage. Then we fabricated the device. For the fabrication of the device, we use methods deposited over the PTFE film, and then we also deposited metal electrodes above and below the PVD zinc oxide film, and then we made a Bruce rectifier, and then we will take the output of our uh, device. So here is the result. But before, we fabricated three different devices. One is the from by using the PTFE with zinc oxide PVDF film as it is. Another one is we fold the PVDF zinc oxide film, positively fold, and another one in the PVDF zinc oxide, we negatively fold the sample, and we check the output performance of these three devices. So when we measure the output voltage, it's found to be that when we use the positively fold PVDF zinc oxide film, the output performance increases, but when we use this negatively fold film, the output performance decreases. This is because of the fact that, and as Professor Zhang already showed in his invited talk also, that when we do the polling, the electronic characteristic energy level of the electrons in the PVDF changes. So, triboelectric effect, right now there are three main theories. One is electron transfer theory, ion mass transfer theory, and mass transfer theory. But right now it is widely accepted that electron transfer theory is one of the widely accepted theory. So it is said that when we change the work function of the electron, when we change the characteristic energy level of the electron, if there is a very much gap between the PTFE and the PVDF, then there is a greater chance of transferring the electrons from PVDF to the PTFE. So because of the positive fold, there is increase in the characteristic energy level, which leads to greater probability of the electron being transferred from PVDF to PTFE. That is why we are getting more enhanced output performance in the case of PVDF zinc oxide with positive fold. So here we are just showing that by the advantage of using this ferroelectric polymers as a one of the active methods for triboelectric nanogenerators is that when we change the polarity, when we change the polarization instead of that film, we can control the output performance of the triboelectric nanogenerator. So in the area of energy harvesting, it is good also, but when we use this triboelectric effect in the electronic devices, this is we call it tribotronics, where the triboelectric effect is used to control some transistors, some gates. There, it will be very useful in order to implement this concept that we can control the output performance of the triboelectric effect just because of the polarization instead of the uh, triboelectric material. So that is the main conclusion of our work. So we successfully prepared the zinc oxide PVDF film, which was much enhanced surface roughness, hydrophobicity, and triboelectric effect. We fabricated the triboelectric generator coupling with PTFE, and the polarization state of the film is found to be affecting the performance of the triboelectric generator, and the positively poled genocide PVDF films were give a maximum open support voltage of 83 volt. So I also try to explain how the change in the polarization leads to the change in the performance of the triboelectric generator. So I would like to acknowledge the Department of Science and Technology for providing me the inspired fellowship for my PhD. And I would like to thank Nanoscale Research Facility at IIT Delhi for giving us this characterization and preparation. Thank you.
Thank you, Dr. Singh, for a very nice, useful presentation. Are there any questions? There don't seem to be any in the chat box. Nothing is there. Okay. So I think we don't have any questions. So thank you for finishing well on time. Thank you. Let us go to the next talk by Dr. Ankur Solanki of Pandit Deendayal Upadhyaya University, Gandhinagar. So, Dr. Solanki, are you there? Hello? Dr. Solanki?
Dr. Solanki, please unmute.
Solanki?
He's muted.
Yeah, yes, sir. I can hear. Can you hear me now, sir?
Yes, yes.
Okay.
I'm so sorry there because I was unmuted accidentally. Yeah.
Okay. So, please start, and I'll give you, after 12, 13 minutes, I'll give you a signal. Thank you.
Okay. Thank you very much, Professor Vikram. And I would like to thanks to the organization committee first to giving me opportunity to present my work here. I'm Dr. Ankur Solanki from the Department of Physics, Pandit Deendayal Petroleum University, Gandhinagar, Gujarat. So today I'm going to present my work on the solvent additive in perovskite solar cell, which is going to enhance its efficiency and stability. I would like to thanks to Professor Ashish Garg first because he has introduced the development of in perovskite solar cell fields already. So I don't need to involve all these things again. But before that, going because my perovskite structure will be involved in my further presentation. So generally the perovskites has the structure of ABX3, which is the I'm talking about the hybrid perovskites. So where A is the organic or inorganic cations such as cesium, methylaminum iodine, and formamidine iodine, while the B is metal cation, while X is the halide cation. So if we see the structure of the perovskite here, the organic cations or A cation is surrounded by the 8 PBI 6 octahedral structure. So the beauty of this material is that it can be tuned from the 3-dimensional perovskite to 2-dimensional perovskite, 1-dimensional as well as 0-dimensional. It based on your application and the requirement of the perovskite. So other than it's definitely it's a low cost, easy to process, and wide range of the family. So if we talk about the applications, so the photovoltaic is the well-known application of this perovskite, which the efficiency is going more than 25% already. While it is also being used in the field of light emission devices, thin film transistor, memoristor, detectors, and many more other devices. So now, as Professor Ashish Garg has mentioned, that solvent additive is a very nice approach to enhance their stability and the efficiency of these postcard source cell. So here, what we have done, we have used the D2 as the this is the deuterium oxide as a solvent additive in the postcard solutions to enhance the stability. So we use the triple cation postcard which MAFACS, and we added a different amount of the D2O in the solution and in spin coated the postcard thing on the glass. Here we use the inverted device structure, which has like PTA as a whole transporting layer and BCP C60 as an electron transport, and for the silver as a counter electrode. So if we can see here the efficiency of the, or we can say the characteristics, so the efficiency of the postcard solar cell with the 1% due to is higher than the reference devices. As well as if we can also very closely, we can see the efficiency of the D2 added devices also further higher than the H2 devices. So if we relatively compare here, as we include the amount of the D2 in the postcard solution, the efficiency keeps increasing and it is optimum at the 1% D2 additive. While on the further addition of the D2O, the effect is counteractive and it start degrading the performance. And it goes a very low performance at the 4%. And our highest performance was very close to the 20% efficiency. Okay, so other than that, if we compare the device stability, because this is going to the main breakthrough over here, the stability of the postcard solar cells should also be very good. So if we compare with the reference, even with the 1% H2 devices, the devices prepared with the 1% D2 shows the very high, strong stability compared to other devices. Even this performance was measured under the continuous illumination of one sun. So the devices are also stronger with the additive. So now the reason, now we need to find what are the reason that the devices are getting the better stability and the better performance. So we looked into the X-ray diffraction pattern, and relatively we do not see any significant difference in the X-ray diffraction pattern from the all the samples added with the different considered D2O. But if we look into the very closely, the full width half maximum for the 1% D2O is drop, and it is the minimum. It shows that crystallinity of with 1% D2O is improved in that structure. Question comes, what are the mechanisms behind it which can influence or increase the PC in these devices? So very first thing, that if you look into the very carefully, the D2O is the polar solvent. So it can give a strong dipole-dipole interaction in the inside the solution, and it helps to the complete dissolution of the lead iodide and lead bromide, which is generally is not complete dissolution when we are not using any solvent additive, and it creates a defect in the postcard film. While if we also looked into the D2 solvents has generally 101 degrees centigrade as the boiling point, while the other host solvent which were used as a DMSO and DMF, which has the higher solvent. So there is a variation, this is a mixed solvent now, and the variation, and there is a variation in the evaporation rate which can smoothen up the thin film. Other than that, we assume that D2O might also get absorbed at the grain boundary, and it works as a healing agent in the postcard film. Other than that, if we looks into the PTA is the hydrophobic in nature. And while we add the D2O in the postcard film, it is discretely dispersed on the PTA layer. And what is up that it gives the, it helps to interfiltrate the MA and FA and to modify the interface and for the better connectivity of the charge transfer. So it can help to the better charge transfer properties also to give the higher PC in that devices. So now we also looked into the absorption and morphology, and there was no much variation in the devices. So further we looked into the optical properties, we looked into the photoluminescent property. So we excited the thin films at the 600 nanometer laser beam and collected the PL. And we saw then when the PL intensity in the 1% D2O devices is much higher compared to the other. It indicates that there is a high free charge carrier or more free charge carrier in case of the 1% D2O added thin films compared to other devices. And these are free charge carriers. And in case of the devices, these free charge carriers can be easily extracted to give the higher efficiency in these devices. Okay, so further we looked into the trap density in the device and how much is the trap density devices, because we assume the trap density has reduced. So for measuring the trap density in thin films, we conducted the fluence dependence PL steady state PL, and we plotted a charge carrier intensity versus the PL intensity. And we fitted these observations to the one-dimensional defect density equations. So we can here look over here in reference devices, we find only 2.5 10 to the power minus 17 per centimeter cube the defect density over here. But on the addition of the 1% due to the defect density is significantly dropped to the 0.7. So whatever we are expecting that the D2 is helping to suppress the defects inside it, that has been proved here by the steady state PL measurement. The defect density is significantly suppressed, but on the further resolution of the water, the defect density is further improved, and this is counteractive our photovoltaic properties, and the photovoltaic properties are deteriorating. And in case of the 1% of the H2O as well, it goes to similar to the 4% D2 additive. So now we also further looked into the PL lifetime, because that is a direct indication of our VOC as well as the photovoltaic efficiency. If we see here, the PL lifetime of the 1% D2 is also significantly higher compared to the reference samples. Okay, so here we confirm that 1% D2 is suppress the defect sites, and while the higher fraction of the D2 is introducing the more traps inside the thin films. Okay, now the another parameter which is going to be very important in case of the perovskite solar cell, but which is the charge carrier diffusion. Charge carrier diffusion length. So if the charge carrier diffusion is much lower, the efficiency definitely is going to be much lower. So to measure the charge carrier diffusion length, we use the time resolved photoluminescence spectroscopy. So in case of we here the time resolved, I mean lifetime of these films are measured and due to by back reflection geometry, where to measure the lifetime case of the HTL and the ETL. It means to measure the lifetime of the electron and holes, we coated a HTL layer on the top of the perovskite layer. Why? And in case of the for to measuring the electron lifetime, we coated the ETL layer on top of the perovskite layer and measure the lifetime in all three cases. And we fitted the lifetime to this one-dimensional diffusion length equations, where we assume the thickness of the perovskite layer is 400 nanometer, and we calculated the diffusion length. We observed that the diffusion length in case of the 1% D2 additive is also significantly improved, and it is also much balanced, right? So now it is also proved that the diffusion length in case of the perovskite solar cell with 1% D2 is improved, and while on the further addition of the water, it is decreased. So that's clear now that it's a photovoltaic efficiency. The D2O is improving the optical properties or reducing the defects inside it to affect their charge carrier recombination dynamics. Specifically, it is decaying or suppressing the trap assisted recombinations. So now the question is what the D2O is going to the chemically affect over the perovskite thin film. So if we see, as I discussed, generally the D2 has the 101 degree centigrade as the boiling point, while our host has, and while we anneal the perovskite thin film, we generally anneal our perovskite thin film around 100 degree centigrade for approximately 1 hour. But if for the longer time period, we do not assume the D2 will remain inside the thin film. So to confirm this, we measure the Fourier transform infrared spectroscopy, and we saw a observation of the one peak band over here between 23037 to 230 2360 centimeters, and this band is due to the presence of the deuterium inside the perovskite thin film. So it confirmed even though after heating a 1 hour of thin film at 100 degrees centigrade, deuterium remains present inside the perovskite thin film. Now, then what happened to the D2O? Where it is D2O going in there? So there is a two possibility of the deuterium. So either the D2O molecules are penetrate inside the perovskite structure. So they are sharing the A cation side with cesium, methylammonium iodide, and formanium iodide, and remains inside the perovskite. And it happens during the processing or spin coating or annealing of the perovskite film. There is a one possibility. The another possibility is that there is an exchange of the hydrogen and deuterium, right? So there is a and it could be from either from Fa side or Ma side. So there is another problem. So to further to identify whether it is the exchange is towards the formanium side or it is from the methylammonium, we conducted the solid state NMR. And we found that based on this observation, we found that basically the isotope exchange process is occurring towards the Fa side. And if we whether it is from the CH side or towards the NH side. So if we compare it here, the binding energy for the CH, okay, and CH and the NH, the binding energy is much higher in CH compared to the NH. So there is a high chances there the isotope exchange is occurring at the NS site, and that has been proved in the solid state NMR. So, and now another observation we observed from the solid state NMR, that there is a change in the FAMA composition in the resulting perovskite thin film while we are adding the D2 in that film, and that is also influencing their optical and electrical properties in the perovskite source. Now, to further confirmation of it, we have conducted the DFT simulations to to know more about it. So the main question is what is happening to the electronic properties of it, right? So if we compare with the hydrogen and the deuterium, they have same electronic charge. If they have same electronic charge, there is no change in electronic configuration. That's why the band structure and density of states remains the same either in case of the ND, ND2, and ND or ND2, either in the FA or MA side. So there is no change. Now, but if we relatively compare in case of the mass, the MD, the deuterated deuterium has the higher mass compared to the hydrogen. So in case of the deuterated sample, the vibration energy is much higher compared to the vibration energy of non-deuterated sample, or we can say the reference sample. And this is occurs due to the stronger bonds of the ND and ND2. So now we have further compared to the phonon dispersion spectra. So we simulated the phonon dispersion spectra for completely deuterated FAMA system and non-deuterated FA system. Okay, so if we can see here, usually in the vibration in these perovskites at the low frequency, these are dominated by our halides, lead halides. So it is dominated. But in case of the higher vibration at the higher frequency, these vibrations are dominated by our organic cations, which is Fa and Na. And in either of the case, if we see the vibration in deuterated samples are lower than the vibration due to the non-deuterated samples, right? So it means the vibration in the vibration like crystal vibration, we can say it is always lower when the deuterium is added into the perovskite, while if it is not added, though the vibration is higher, and so it helps that therefore it is decreasing the phonon frequency of the PBI6 network, and it can help to stabilize the PBI6 network. So yeah, that's the advantage also. It's helping to stabilize our perovskite. So these vibration properties has also been simulated using the DFT, and it shows that it is very well compared with our experimental findings from the FTIR spectroscopy, right? And this has been done. Okay, so here I summarize my presentation that D2O works as a solvent additive for the triple cations based perovskite solar cell to enhance the stability and efficiency in the solar cell. Specifically, we see the partial deuteration of the Fa is more important to suppress the charge carrier recombination in these devices. And other than that, there is always a judicial selection of the solvent additive and organic cations, because in most of the case, it has reported when the deuterium is added to the MAPI system, the efficiency is always dropped. That's why there's always a judicial selection of the solvent additive and organic cation. So I would like to thanks for my Professor Samsir Chan from the Nanyang Technical University and my collaborator from Dr. Mehdi and Dr. Ching Chong from MIT US, Professor John V. Hanna from Warwick University, Dr. Si Chang from NTU Singapore, and Dr. Nirvan Bawi from IST Singapore. Okay, thank you very much. So any questions?
Thank you, Dr. Solanki, for a kind of interesting idea, adding heavy water. There is a question from Mr. Atanu Purukasta. Will D2O as additive solvent will increase the stability of lead-free perovskite? You have a lead-free perovskite.
Yeah, there is a high chances that it may increase the stability in the lead-free perovskites as well, because it can penetrate into the perovskite structure and it suppress the vibrational energy of it, and that's why it will help to increase the stability.
Okay, thank you. I'll ask one.
Yes, sir.
how much the cost of perovskite soda, how much more expensive will it become?
Hello.
Can you understand? My question is, how? What
Yes, sir.
about the cost
Yeah.
of the cell? How much more it will become
Uh,
costly?
sir, if we looked into there's a structure which we are using, because if we see the cost analysis, specifically in case of the regular structure, we can say, normal structure which consists of a spiro. So these are more costly compared to the inverted structure, relatively we talk about. So here
I
what
see.
we are using, relatively the cost is more, this structure which are inverted structure is a cost effectively compared to the other structure which is the regular structure. So of
Okay.
course the people are looking into the further cost down.
Very good. Okay, thank you. Thank you for finishing well in time.
Thank you very much.
Thank you very much. Now I invite the last speaker of this session. We are running about 10 minutes behind time. Next speaker is Ms. Jyoti Sinha from Icee Bangalore, talking about passivation of silicon interface with ultra-thin tunneling SiO2 layer with rapid thermal oxidation. This is very interesting for me because my PhD from 40 years ago was on ultra-thin current tunneling SiO2 layers. Okay, Dr. Sinha. Jyoti Sinha, please.
That's what I felt, sir. You feel it now after 40 years.
Yeah, after 40 years becoming useful.
4 decades.
Yes. Okay.
Hello, Jyoti.
Yes, sir.
Okay,
Sir, I'm trying to share my.
yeah, you share the screen.
Please go ahead.
Sir, just having a trouble with sharing the screen. Good afternoon, everyone. Thank you for providing me this opportunity to present my work over here. My name is Jyoti Sinha. I'm working as research assistant in Center of Nanoscience and Engineering, Icee Bangalore. Today, I will talk about passivation of silicon interface with tunnel oxide using rapid thermal oxidation. Am I audible?
Yeah, please go ahead.
Oh,
I
okay.
can hear you.
Okay.
So,
So I will briefly talk about the motivation behind pursuing it and why I have used thermal oxidation and what process steps have been taken to improve passivation, and I will conclude with the conclusion. So going ahead, in crystalline silicon solar cell, a group from Germany has demonstrated TOPCon solar cell with efficiency of 25.7% in 2017. So which is the state of the art. So what they have done in this TOPCon, there is a tunnel oxide and this is a doped silicon thin film, which is known as tunnel oxide passivating contact. So what is the use of this TOPCon in this stack? So they have used this TOPCon to provide passivation and use it as a contact. So they have achieved a efficiency of 25.7%. So therefore, to further improve this TOPCon, we can either improve the quality of tunnel oxide or we can play with this doped silicon. For this work, I will only focus with this SiO2 to reduce the recombination losses at the silicon SiO2 interface. Since Tunnel oxide provides better passivation and allow carrier to transport. So I will talk about these properties in further slide. As I have mentioned earlier, I want to improve quality of SiO2. So first we need to assess the criteria on which the quality of SiO2 will depend. So first there is thickness. So for current generated in solar cell, it must pass through SiO2. And as we all know, it is a insulating in nature. Hence, for this, the thickness should be thin enough so that current could pass. And it has been reported in the literature that this thickness should be less than 2 nanometer. And the state of the art device has thickness around 1.5 nanometer. The second parameter we should focus on is the passivation quality. How good quality of passivation we can achieve so that the recombination losses at interface will be minimum. As we know that what parameters we have to focus on, so I will move towards the ways to get SiO2. So there are number of ways to get SiO2, but primarily thermal oxidation and wet chemical oxidation has been used. And the state of art device which I have shown earlier, they have used HNO3 to get the SiO2. So in my case, I will be using thermal oxidation. So I have used rapid thermal oxidation and used N2O as an oxidant to get SiO2. So why I have used rapid thermal oxidation? Because it has been well known that rapid thermal oxidation gives better electrical characteristics than classical furnace growth film, and the most important part is we can control the thickness of SiO2 while rapid thermal oxidation, which might be difficult while doing classical furnace growth. The another parameter is why I'm using N2O, because we can also use oxygen, but in comparison to oxygen, N2O is a stronger oxidizing agent and it gives more free nascent oxygen. So hence we are getting more free nascent oxygen, so we are able to have more uniform SiO2. Hence we have used rapid thermal oxidation and N2O to get SiO2, and this has not been done earlier in this TOPCon solar cell devices. So for growing SiO2, I have used N-type silicon substrate with 100 orientation having resistivity around 1 to 10 ohm centimeter. So before growing SiO2, Si substrate was subjected to standard RCA procedure, and to remove the native oxide, the Si substrate was immersed in HF. So to grow the SiO2, this rapid thermal process system has been used, and the block diagram of this is given over here, where there are different kinds of gases are connected to this reaction chamber, and this is a pump and a vent, and the halogen lamp is used for the rapid heating. So this is the flow process of the rapid thermal oxidation. So as we can see over here, this is at room temperature, and it has been evacuated. Then the lamp was turned on and it was ramped to the desired temperature. In this case, we have used 3 different temperatures, and the whole time for 3 different temperatures was 30 seconds, and this was done at near atmospheric pressure. And when the process has been done, ramp was cooled naturally, and we vent it and we take out the sample. During all this process, all has been done in the N2 environment except where the oxidation has been done. So as we can see over here, with different temperature, we are getting a minimum thickness at 600 degrees C. And this thicknesses has been measured using ellipsometry. since we are getting minimum thickness at 600 degrees C for 30 seconds, so in my further slide, I'll be using this process condition to check the further quality of SiO2. So to check the passivation quality of grown SiO2, first I have grown dry oxide at 1000 degree C of SiO2 100 nanometer, and then I use MDP to detect the lifetime of this sample, which comes out to be 60 microseconds. Then I removed etched the SiO2 from one side and grow the thin oxide using rapid thermal oxidation for at 600 degrees C for 30 seconds, and then measure the lifetime. So as we see in this picture, there is variation in the lifetime with different regions, and the lifetime is also very less as compared to SiO2, because as we have decreased the thickness, the passivation quality of this sample has decreased. So here there is a need of further improvement. So first, to make further improvement, we need to figure out what possible reason are for low lifetime. First, we have grown our oxide at 600 degrees C, and it is well known that fixed oxide charges can get into the system due to different oxidation process. So this is might be a one reason, and the another reason is the interface between silicon and silicon oxide, a suboxide region which could promote interface trap charges, which might decreasing the passivation quality of our SiO2. So to further improve lifetime, annealing has been done after growing thin SiO2. So why we are doing annealing? We are doing annealing because after annealing at high temperature, fixed oxide charges will decrease. So in this process, we can see earlier I was only doing oxidation in N2O environment, but after N2O environment, when the system cooled down, I again ramp up it to 900 degrees C and hold it for 60 seconds, and then it cools down naturally. So just one question to arise over here: why we are stuck to only 900 degrees C? Because it has been found in the literature that when we go beyond 900 degrees C, ultra thin oxide have some broken bonds of SiO2, which was shown in research through TEM. So therefore, we have restricted ourselves to 900 degrees C. So this problem, so this annealing can fix our problem of fixed oxide charges, but to further improve the trap charge at interface, we have done forming gas annealing at 450 degrees C for 30 minutes. So to see the effect of passivation quality after end-to-end forming gas annealing, we again done the lifetime measurement, and what we can see over here is there is improvement in the lifetime which is 32 microseconds, and the regions and we can also see the clearly visible distinction between the different regions of the substrate. So this proves that after end-to-end forming gas annealing, the passivation quality of this thin oxide has been increased. But as I have mentioned earlier, there are two parameters. First, it has to be a good passivation quality, but it also allow the current to pass. Therefore, we have done electrical measurement of this thin SiO2 after end-to-end forming gas annealing. So for this, we have done optical lithography to transfer TLM structure to measure the contact resistivity on the same structure we have measured the current. So as we can see in this current, at 1 volt, the current is around 0.2 amps per centimeter square, and for a typical silicon solar cell, the minimum current we need is 40 milliamps per centimeter square. So we can say from here that with this thin oxide, we are able to flow sufficient current through the sufficient current to our devices. And using the TLM structure, we have calculated contact resistivity, which comes out to be 0.84 ohm centimeters square. So in the conclusion, we can say that we have grown thin SiO2 at 600 degrees C for 30 seconds, and the passivation quality has been improved, and with electrical measurement we are able to say we have achieved sufficient conductivity. I would also like to conclude that there is further much work is needed, because more we need to study about the carrier transport in this thin oxide, which is still not discovered, which will be my future work. So I would like to thank all the participants over here and professors, and I would like to my advisors for guiding me in this project. Thank you.
Okay, thank you, Jyoti, for finishing well in time. Uh, I see in chat box there is no question so far related to your talk. So
I have one.
let's just make one comment. Is there anybody else?
I have one question, sir.
Please go ahead.
Hello, Jyoti.
Yes, sir.
Somewhere you mentioned suboxide, right? SiO2 you have been talking, and then you said suboxide.
Yes, sir.
How to distinguish that the thin layer, whatever you are growing, it is SiO2, SiOX? And
So,
what are the...
sir, what measurement I have done, it will be not easy to distinguish with the measurement which I have done. So what we can do is we can use a TEM which can show a clearly distinction between which is the SiOX layer and SiO2 layer.
How?
We can use we can use stem layer, or we can use stem layer, and we can use XPS also to determine at which depth level the Si valence bond has changed.
Okay, XPS is okay, but TEM you were saying, can it distinguish based on the contrast? I don't know. That's what. So basically, passivation according to you is a SiOX or SiO2, which is required.
Sir, since SiO2 is required, but it is very hard to eliminate the native oxide while transferring substrate to that furnace. So there is always a layer of SiOX between the Si and SiO2. Therefore, we have introduces the forming as annealing to deplete those interface trap charges.
Okay.
Okay. So I have one question or comment, Jyoti.
Yes, sir.
This, first of all, you said your thickness you are determined by ellipsometry.
Yes,
So
sir.
the comment in that is that the thickness of 1.5 nanometer, if you do by ellipsometry, because that assumes parameters of SiO2, and you don't know whether you have SiO2. For 1.5 nanometer, large part will be SiOX. So the thickness is likely to be different than what. Okay,
Sir,
so
I agree on.
let me complete. You also have done it by NO2. So there's likely to be nitrogen also incorporated in that to some extent.
Yes, sir, I agree with your point that the exact thickness of SiO2 could not be determined using ellipsometry. But on the part of N2O, I think a further experiment is needed to be done, because the incorporation of nitrogen is usually done at a higher temperature. That is why when we do oxynitridation at 800 degrees C or 900 degrees C, it becomes slower in comparison to oxygen. So in this case, we need to do XPS to see if there is some incorporation of nitrogen or not, to confirm nitrogen has whether incorporated in this SiO2 or not.
Yes. Okay, that should be done. And of course, effective thickness you can use measure using CV method also. As far as transport through this tunneling layer, I don't know if you are aware, I have a paper in 1977 in solid state electronics. Okay. So
Okay, sir.
on this tunneling oxide of 2 nanometer thick, how the tunneling takes place. So
Okay,
you
sir.
can look into that. Solid state electronics, 1976.
So,
Very
sir, you mean trap assisted? What was the conclusion, sir?
yeah, assisted.
Trap assisted.
Yes, it has to be.
Sir,
So
so
it's a
this
very
is
typical
where
calculation.
So for that you need SI volts only, if it is trap assisted.
Yeah, its traps are there in the at the interface, and in the side, of course, is assumed to be some sort of effective barrier. You don't know whether what kind of barrier is this at that level, and so. But its surface states are also there, which are also distributed within 2 nanometer, within a few angstroms. So that study is for 20 to 50 angstrom. Those days we used to call angstroms. Uh, anyway, please look into that, Jyoti.
yes, sir. Actually, I have mentioned also that carrier transport, this thin oxide is need to be explored because there is some paper which have done simulation through it, and they have showed the existence of pinholes in this SiO(X) layer or SiO2 layer, where they have said that it can enhance transportation conductivity, but can also degrade with a minimum uh, density. So in this area, no experimental work has been done. So this is a future prospect to do.
No, no, no. The point is that a lot of theoretical and experimental work was done at that time. My professor, Professor Dalke, Dahlke, has a series of PhD students. I was one of them. Had working on this ultra thin oxide layers. Okay, there was a Leo Freeman, some Rescar, myself, somebody else also. So there is a lot of literature in 70s which people have forgotten. Okay,
Okay, sir.
you
Yes,
please
sir.
look into that.
Okay, sir.
And there was some Chinese group, Shuchun करके. He's also doing this lot of work.
See, solid state electronics, very, very good papers found 1970, 80, all talking about this.
Yes.
While trying to understand amorphous, I am looking SiOX, this passivation.
Okay.
Okay, sir. Thank you. Thank you
We'll
for
have
your.
to work on this thin oxide at that time for whatever reason. Okay, thank you. So this session is now complete, and I hand over to Dr. Vamsi if he has any announcements.
Sir, thank you, sir. Thank you, sir. First of all the speakers and I think Professor Garg is still there. Thank you, Professor Garg, for your time and presentation. Sir, I would like to thank you, sir, for you also.
Okay.
Spending more than 2 hours here. And in 10 minutes, we need to start, supposed to be 30 minutes, but now it reduced to 9 minutes. Another session will start. Professor Avasti will join for that. Thank you, sir.
Thank
And
you.
good afternoon.
Good afternoon.
Once again, thank you all the speakers. Hello, Dheeraj. Hello, Dheeraj. Shrestha.
Good afternoon, everyone. Sorry for starting the session a little late. Am I audible? Hello.
Yes, yes, we can hear you, Professor Avasti.
Okay, thank you. Yeah, so thank you. Welcome you all for the afternoon session. I was having a little trouble finding the WebEx link, so apologies for that. Request. There's some echo.
I think the first talk is by Shabal. So it's my pleasure to introduce Shabal. Shabal, are you online?
No, that's what I'm not seeing him in the participants list.
Okay, let me call Shabal. Just give me a minute. Okay, so Shabal is having some technical issues. He's requested me to switch his slot. So if it is okay, Ashish, can I request you to go in his place?
No, she's actually completed morning.
I see.
So he somehow is still hanging around.
I see.
I've already
Okay,
finished
sorry.
myself, right?
No, sorry. My apologies. Jatin Rath. My apologies. Professor Rath, can I request you to go instead?
No, he's in, I think, Netherlands. I wish he will, maybe in few minutes he should be joining. He's
Okay.
also.
So I think we are just waiting for our invited speakers. Are the oral presenters here? Mr. Suren, are you here? Okay. Or Miss Avriti? All right then. I guess we have nothing to do but wait then, because none of
Yes.
our speakers are here. Okay, interesting.
This is actual, it seems lunch time, official.
This is the time you feel that it's good that you're sitting at home.
I was surprised. No one is logging in. I am waiting someone to log in.
No, so what happened with me
I
was
was
that.
logged in for a long time.
No, so what happened with me was that I misplaced the WebEx login, and I kept going to the YouTube, which was not the point. So finally, I found the WebEx login.
Yes, Suren is there, Professor Avasti.
Okay. Okay, Mr. Suren, is it possible that I can ask you to go the presentation first?
Hello.
May I request others to maybe mute?
Yes, Suren is there, Professor Avasti.
Mr. Suren, is it possible that I can request you to please present before time, because two of the invited speakers are having some issues technically.
Hello, sir. Can you repeat? I can't hear you actually. There is a lot of echo.
I see. I was requesting you that is it possible for you to start your talk first? The invited session speakers are having some technical issues.
So maybe we can swap your slot with them.
Now, right now you are saying?
Yeah,
Now
right
you are
now.
saying?
Yeah.
Yeah, just give me some time so I can share my presentation.
Yeah. Sure. So whenever you can get started.
Yes.
Just let me know so I can introduce you.
Fine. Am I audible properly?
You are audible properly.
Okay, thank you. So just give me some time. I can start my presentation. Just please let me know if the screen is visible properly. Hello.
We can see that.
Yeah, we can now see your presentation, please. Okay.
Okay. So just
so
let me know when can I start.
Yeah, sure. Just 1 minute. So, okay, so some change in schedule. Welcome to the session on photovoltaics and energy harvesting. I hope you had a nice lunch. So the invited speakers have some issues. So we are going to start with the talk that was supposed to be at 2:30. This is a talk by Mr. Suren Patwardhan from IIT Bombay. And the title of his presentation is Performance Evaluation of Hole Selective and Passivating Moly Oxide Layers on Silicon, a comparative study of ELD in evaporation. Mr. Suren, thank you for joining us, and start whenever you can.
Thank you, sir, and good afternoon, everyone. I'm Suren Patwardhan from IIT Bombay, and this post-lunch presentation, I'll be showing you the results of our work on the evaluation of hole selective and passivating molybdenum oxide on silicon, which we tried to deposit by two routes, that is ALD and thermal evaporation. And this work is just a presentation of the outcome of these two routes. If you look at the trends in silicon-based solar cells, so from the conventional homojunction-based solar cells, which consist of a P-type absorber layer, now it is slowly moving towards the N-type absorber layer. With the heat cell, popularly known as heat cell, it has already surpassed the conventional solar cell in terms of efficiency. And the main feature of this heat cell is that there are two dedicated layers for the two main functions of a solar cell. One is the passivation and the other is the carrier selectivity. So both are achieved by using amorphous silicon layers, intrinsic amorphous silicon layer for passivation and the dope amorphous layers for carrier selectivity. Now this is the actually configuration which has produced the highest efficiency of silicon based solar cell so far. But then there are also parallelly there are some issues talked about it, particularly regarding the parasitic absorption losses in the top doped amorphous silicon layer. And as an alternative, there are many metal oxides came forward, moly oxide or vanadium oxide or tungsten oxide or even nickel oxide. People have already demonstrated it. And in fact, by using moly oxide in place of the P plus amorphous silicon on the top, efficiencies exceeding 20% have already been reported. Now the next, so this configuration is basically called as a dopant-free carrier selective contact cell, because these metal oxides are not typically doped like those amorphous silicon layers, and they also have a very large band gap, which results in an overall gain in the EQE. Then the next step in this dopant-free carrier selective contact type solar cells is to bypass that amorphous silicon layer altogether, and because it has been already shown. Hello. Yeah, because it has been already shown that the moly oxide itself can work as a good passivating layer for silicon. And so the idea is to use the moly oxide layer for both hole selectivity and passivation in a configuration which is called as a amorphous silicon free solar cell. So basically our work is also based on a similar kind of a configuration, where we deposited that moly oxide by two routes, that is thermal evaporation, and the other one is atomic layer deposition. Yeah. Yeah. So typically, if we consider this, the carrier selective based, the dopant free carrier selective based solar cells, they typically have a hole selective materials like molyoxide on one side and electron selective layer as another material like TiO2 or LiF on the other side. But then since we wanted to vary the deposition technique of molyoxide, we just wanted to focus on the performance of molyoxide, and then we actually decided to have some kind of a conventional structure at the backside which will act as electron selective layer. And so for that purpose we actually had this N plus layer at the back, which was formed by traditional POCl3 diffusion. So we actually did this phosphorus diffusion in an N-type silicon, and we started with this 5-inch N-type silicon wafers, and these are ASCAT wafers, so we had to follow that SDR and all procedure. These wafers were not textured, so whatever results I'm presenting, these are for the non-textured wafers. So our work is still going on, which we can include the texturization step also in between. But basically, after doing that phosphorus diffusion, we get this N plus back surface field, which will act as electron selective layer for us. And then after that, we etched back the front layer to get back that N layer again, where we deposited this molyoxide by two techniques. And then that is the schematic of the cell. If that screen, you can see that typical schematic for our cell, where the other layers followed after molyoxide. Now this, I have a little problem in switching this.
There's a little delay.
Delay, yeah, yes.
Yeah.
Just please bear with me. Okay. So basically, when we think about this direct deposition of molyoxide on silicon, in order to use it as a passivation layer also, in addition to hole selective layer, there are certain advantages and disadvantages. So in terms of the advantages, it clearly offers a low cost processing step, because we reduce some number of steps of depositing these amorphous silicon layers, and at the same time it also avoids the maintenance and the cost which is related with the use of these hazardous gases precursors. On the other hand, the molyoxide has not yet achieved the passivation quality which is achieved by using amorphous silicon layers. So that ultimately results in this lower open circuit voltage of these devices. I'm talking about molyoxide directly deposited on silicon. And so ultimately, so far, if we just look at the literature, so there is about a lot of difference in the efficiency, and this difference in efficiency has mainly come up because of the lower open circuit voltage. So if you compare their cell characteristics, then the current density is almost the same for solar cells using amorphous silicon as a passivation, and for solar cells not using amorphous silicon as a passivation. But the main difference has been about open circuit voltage, where the later one has open circuit voltage smaller than about 100 millivolt. Okay, so there is a large gap actually to follow. Now there are different deposition methods used so far for molyoxide, out of which the thermal evaporation has been the preferred one, not because it is just cost effective and it is simple, but at the same time it has also produced results with a very high efficiencies. But we actually wanted to compare this results of this thermally evaporated molyoxide with some other technique. So we selected atomic layer deposition, and then the one uh, uh, thinking behind using this atomic layer deposition is to take the advantage of its conformal deposition, which is more or less natural in this ALD process. The other reason was the in thermal evaporation we don't have any control over what will be the stoichiometry of moly and oxygen in the deposited film. Now, why this stoichiometry is important is because if you consider this direct deposition of molyoxide on silicon, then it is the band bending in silicon which happens. So that ultimately decides what is going to be the passivation quality of this molyoxide, and that is in turn governed by the work function. And the work function of this molyoxide is largely dependent on the O2MO ratio in the deposited film. Now, it has been observed that when we deposit molyoxide by different techniques like that thermal evaporation or ALD or solution processing, the moly oxide has got a lot of intermediate states from MoO3 to MoO2. And then some of these states are lying close to the conduction band and which actually are helpful. Some of the states are little deep into the band gap and which are actually hampering the device quality. So it is actually very important that when you deposit the film, then whether you are able to control the phases of this moly oxide. And so that was the one reason for going for ALD. With thermal evaporation, this kind of a control, stoichiometric control, is not actually possible. So we actually tried with two precursors of moly oxide, which have been tested so far. One is this hexacarbonyl based, and the other one is this butylamide based. But we did not get a stable film using this butylamide based precursor for moly oxide. And in fact, the carrier lifetime was also not stable. And then we tried to do some devices with this, which ultimately resulted in a low barrier Schottky kind of a response. So most of our devices are actually made from this hexacarbonyl based precursor, and ozone was used as a precursor for oxygen. And then we actually tried to optimize this process. This 3 pulses of the moly precursor and 2 pulses of the oxygen precursor, and with a 1 second stabilization period. So the typical reaction which occurs at the silicon surface, it ultimately gives you a moly oxygen and silicon bond, and there is a evolution of carbon monoxide which is carried by the carrier gas. We used argon in our case. Now when we try to compare the XPS of films, moly oxide films deposited by ALD and thermal evaporation, the 6 plus to 5 plus state ratio was more or less same in both. But what we actually observed in this let me see. Yeah. So what we observed in this thermally evaporated films is that after carbon correction, the standard peaks of 6 plus peaks of moly oxide, the 3D peaks. Okay, so they are occurring at the standard values of 236 electron volt and 233 electron volt. Whereas for the ALD film, this actually peaks are a little bit shifted to a lower binding energy side. So this is a kind of indication that there are some reduced states possible in the ALD deposited moly oxide films. Whereas in thermally evaporated film, there is a presence of a screened 4 plus state, but the peak positions they actually tell us that this is having a lesser number of reduced moly oxide states. So this was actually important in order to understand what kind of work function will be there for moly oxide. But when we actually try to measure the work function, we don't have an in situ kind of arrangement. Whenever we measure the work function, we got a value about 5.7, which is actually corresponds to the air exposed moly oxide film. This is a table actually which just compares some of the parameters ALD and evaporated moly oxide films. The one important observation actually which you got is that when we deposited moly oxide films by ALD for different thicknesses. So we try to vary the thickness of moly oxide from about 6 nanometer to 12 nanometer. And then when we change the thickness and when we do it at different times also, there was not much variation in the O2MO ratio when we did this XPS analysis. Whereas for the evaporated film which I shown, so there was a lot of variation. So if I do the evaporation at different times and for different thicknesses, then the O2MO ratio was quite different at different. So there was not that such kind of uniformity which we observed. Same thing happened with the observation with the carrier lifetime also when we tried to measure the implied VOC. So basically, this was important that ALD can actually assist in giving us some kind of a stable O2MO ratio. At the device level, when we actually try to form the solar cells by using that N plus region as electron selective layer at the back, then the ALD based devices that could not outperform our thermally evaporated devices. The maximum current for ALD based devices we got was around 31 milliampere per centimeter square current density. But the main problem was the open circuit voltage for all the atomic layer deposited cells was less than about 150 to 200 millivolt than the thermally evaporated devices. Most of our thermally evaporated devices, they reached 600 millivolt in the light IV characteristics. whereas our range for VOC for ALD devices that varied from 400 to 405 to about 430 millivolt, where the higher VOC was obtained for films which were thicker actually, but then the current was smaller. In now, when we compare the EQE of the both types of cells which were fabricated from ALD MOX and thermally evaporated MOX, we actually observed a significant loss of EQE in the bulk region. Actually, okay, you can see that this region corresponds to the central part, say beyond 600 nanometer. So there is some kind of impurity we thought that has been incorporated in silicon. Now the problem is the silicon wafers which are used for this both routes were the same. The pre-processing was same actually, and it is only the molyoxide part which was different. So then we actually tried to speculate some certain reasons that what could be the possible loss of this EQE in the bulk region of silicon. So we also did this try to fit this data, our dark IV data for both the cells using this standard that two diode model. And what we actually observed is that ALD is slightly deviated from the standard parameters for this N1 and N2. But the major difference you can see over here is regarding this J01 factor, okay, which basically corresponds to the bulk of silicon. And there are quite some reasons which we are trying to work out. Is one is that the surface contaminants may be present during the ALD deposition. So because these are the things which may reduce the passivation quality and which will affect the open circuit voltage, because the main observation in the device characteristics was the low open circuit voltage, whereas the current was still comparable with the thermally evaporated devices. Other reason which we thought was maybe the use of this carbon-based precursor, which is known to change the work function of molyoxide, and again that could be the reason. And the other one is some impurities in bulk silicon. Now, how is this possible? Because the whole ALD process was done at about 175 degrees centigrade, so that is not a very high temperature that the impurities will move into the silicon. But the chamber was actually shared by for different deposition materials also. So one of them was copper oxide mainly, and copper is known to be very highly mobile in silicon. So that could be one reason of getting the low EQE for our devices. The ALD devices, they also showed high series resistance because the MOX films used for ALD devices was a little thinner, about 6 to 10 nanometer, whereas for thermal evaporation we needed to go up to 10 to 15 nanometer. But the series resistance for ALD devices was a little higher, on the little higher side. Okay, this is, yeah. One more observation which we actually found interesting is regarding the passivation quality, or not passivation quality exactly, but regarding the stability in passivation. So when we measure the carrier lifetime using molyoxide films about 30 nanometer deposited by thermal evaporation and ALD, then when the measurements were taken immediately, the thermal evaporation um, uh, films, thermally evaporated films, actually showed a lifetime about 100 microseconds or so, whereas for the atomic ALD deposited films, the lifetime was about 50 microseconds. But then when this remeasurement was done about after about 1 week, the thermally evaporated films were totally degraded, and the lifetime was completely degraded, less than 10 microseconds, whereas there was not significant difference or reduction in the carrier lifetime for the atomic layer deposited film. So that is one more observation which we found with this atomic layer deposition. So with this preliminary results, so let me just conclude whatever work we have done so far is it is quite possible that the ALD can offer a better route in terms of controlling the work function in molyoxide because of the very nature of ALD, and then some of the observations regarding this XPS and carrier lifetime measurements. The low VOC which we observed in our ALD is basically may have got various reasons, particularly the some kind of a contamination on the surface or some kind of movement of impurities, highly mobile impurities like copper in the bulk of silicon. And then, there is a scope that the ALD deposited molyoxide films, we can use it for a precise control of the O to MO ratio of molyoxide films, and then thereby controlling the work function of the deposited film. Okay, provided we are able to protect the molyoxide film from exposure to air immediately after deposition, because there are reports that the molyoxide film, the work function drastically reduces even for a very short exposure to air. But when you deposit this molyoxide film by a precise control like the technique of ALD, and then if you have a provision to have add an overlayer to molyoxide to protect it from air, then that would be the next actually possible step in this particular work. So I stop here my presentation. Thank you very much.
Thank you, and thank you, Mr. Suren, for coming in to keep us on schedule. The paper is now open for questions. I believe you can type your questions is the way we do it. While I see a question, actually, I have a question, Mr. Suren. When you, I missed the details for the recipes for the evaporated one, but the questions are that A, did you do that in oxygen, and B, if not, and what temperature, and does that play a role in the fact that you get degraded surface with the ALD
Yes,
molyoxide?
yeah. Talking about ALD deposition.
ALD versus evaporation. So when you are comparing with evaporation, was there a oxygen present when you are evaporating, and at what was the substrate temperature when you are doing the deposition?
No. During evaporation, actually, we did it in a Globox integrated environment, thermal evaporator. So, which was obviously N2 filled. So, there is a very less possibility of oxygen being present in the evaporated films. Whereas in whereas in ALD, yes, it was actually the ozone based. So that's one difference between the deposition, the two deposition methods actually. The oxygen could be the controlling parameter.
Right, thank you. So
can I comment, Professor Avasthi?
Of course, please.
Okay, Suren, what based on our observations, you see the thermal evaporating molybdenum oxide is basically promoting inbuilt silicon, dioxide, SiOX.
Okay, yeah,
that
yes.
Well proven. So it is also very clear in your case, the open circuit voltage, right?
Yeah, yes.
590. I think that is missing in case of ALD, because if you see the composition analysis, it is very close, right? Small variation in the
yes.
I think MOO ratios.
Yes.
So definitely, somewhere that SiOX is missing in case when you do through ALD.
Yeah. Actually, I don't have the TM of ALD deposited films. I do have the TM of thermally evaporated films. So that's why I did not compare that result also. But that
Yeah,
could
you
have
should
been
do.
the decided what you're saying.
Yeah, cross sectional you should do. I think if ALD is not promoting the unintentional SiOX, so then you are unable to. You have to go through amorphous or
Yeah. Thank you, sir. That's a good suggestion actually. Thank you very much.
So how did you get the work function measured? It's like
no, this was by UPS actually.
UPS. Okay.
Yeah. So these were air exposed films, so we don't have this in situ UPS or XPS.
Thank you.
Yeah.
Okay. With that, let's maybe move on to our next speaker. It gives me great pleasure to introduce Professor Jatin Rath, who obtained his PhD from IIT Madras. He then joined the Utrecht University in 1995 and became a full tenured assistant professor in the research group of physics of devices as part of section in nanophotonics at the Debye Institute of Nanomaterial Science at Utrecht University. He has over 30 years of experience in thin film silicon materials and solar cells and has published more than 250 papers in international journals and conference proceedings. Under his supervision, 17 students have obtained their PhD degree. A very successful career in Utrecht. Professor Rath then joined in 2012, he became the group leader of the physics of devices of Utrecht University at Philips High-Tech campus in Eindhoven. And then in May 2018, he joined as professor at IIT Madras, PV domain in the DST-sponsored DSEHEC project, set up a PV lab and develop heterojunction cell-based single and tandem solar cells. May I request the participants to please mute themselves? There is a lot of. Thank you. So with that, thank you, Professor Rath, for joining us. And the title of his talk is Inline Processing Tool for Silicon Heterojunction Solar Cells and Fabrications. The floor is yours, Professor Rath. You are muted, sir. Please kindly unmute yourself.
Can you hear me?
We can hear you, sir.
Yeah, okay. Sorry. Good afternoon, everybody. I'm actually in Netherlands, so it's a good morning from this side. I'll give it. My talk is about inline processing tool for silicon heterojunction solar cell fabrication. So I'm J.K. Rath from IIT Madras. I was in Utrecht University up to 2018, and we have set up a lab in IIT Madras. I took my lab from Utrecht University and set it up in IIT Madras. And we are having a new project along with a DST project along with BHEL Gurgaon. So that's why BK Pant and Binan Bhadras are the other co-authors for this talk. This solar cell, it's a very simple thing to talk about just to start process. The solar cell was invented long ago, proposed long ago. It took almost 100 years to get the real the solar cell made in Bell Laboratory. And since then, a lot of effort has been made to make it terrestrial use. And there, the argument was that the solar cells are very expensive, so they cannot really compete with the normal fuel fossil fuel energy. But now, if you look at this, the price now is coming down quite a lot. Now it is almost, I say almost 2 cents per watt peak. So this is almost it is cheaper actually compared to the fossil fuel. This has happened mostly because of the crystalline silicon development last many years. And if you look at the slide on the type of solar cells, you see that mostly it is crystalline silicon, whether it's monosilicon or polysilicon. The contribution from the thin films like amorphous silicon or cadmium telluride or CIGS is very, very small. It is the crystalline silicon is going to dominate the solar cell market for quite some time to come. There are basically the ones which you see in the market is basically homojunctions. There are silicon NP junctions basically. 3 new developments have happened recently. One is that PERC type of solar cells, which is basically a version of PERL solar cells, which was proposed by Martin Green in almost 20 years back. So the PERL solar cells, the PERC solar cells, only difference is that this locally diffused this layer is not there. If it's locally diffused, it's pearl cell. Otherwise, it just what you have is P-type silicon with a oxide layer and aluminum metal, and just to fire it, so it will be make contact here at this point. And top surface is actually totally passivated surface. This is called a PERC type of cell, which is basically has now taken over from the aluminum BHF type of cells, and is marching towards nearly 19% average efficiency can be obtained by that. In that, you have also the back contact cells made in these configurations, where you have all the contacts on backside, NP junks, the contacts are N and P are both on backside. So top side is basically then allowing more light to get inside, and some power has showed 25% efficiency by this. So anyway, the PERC type of cells are here to come, is to stay for some time. It's a commercially viable technique, and it gives a good efficiency. And the ones which are competing with them at present, which will come in the future, which will also dominate market in near future, is the two types of cells. One is called tunnel oxide passivity contacts, which is called TOPCon. And here the Jinko Solar has made almost 24% efficiency in the modules. This is actually very similar to PERC cell, except that the top side is totally passivated surface with aluminum oxide, for example, here. This is N-type silicon with a P-type emitter with a oxide layer to passivate, and then you have other layers contacts. The main thing is the backside, you have a oxide layer to passivate, and there is a polysilicon layer which is made by PECVD, and basically a high temperature, if you put a fire it, and then you get a microcrystalline silicon or polysilicon here, and that's where the tunneling takes place. These sort of cells are very attractive because each it's quite a easy operation to make it, and so the efficiency is about 25% has been made, whereas also in the modules 24% efficiency has been made. So this is going to compete, or rather with PERC cells. It will take over from the PERC cell. The other one is called silicon heterojunction cells. These are basically heterojunctions between the crystalline silicon and amorphous silicon. All these PERC cells or TOPCon or heterojunction cells, mainly they focus on the passivation of the crystalline silicon wafer, and whereas there are different techniques by which they do. In a heterojunction cell, basically the passivation is done by amorphous silicon, thin amorphous silicon layer, and the emitter layer, let's say, is amorphous silicon, and the backside silicon, let's say N-type silicon, let's say here the observer, and here you have a intrinsic amorphous silicon of nearly P-type amorphous one, which is around 5 nanometer to 10 nanometer. Then you have TCO layer, transmitting conducting oxide, and the metal contact. Backside, you have a back surface field here with a first amorphous silicon passivation contact, a back surface field, which is a P-type heavily N-type silicon layer, and there is a TCO layer and the backside. So it can be bifacial cells. Sanyo was the one who pioneered this one for a long time. They made the first cells around 1990s, taking over the technology from Osaka University, from Hamakawa. They were to reach nearly, unfortunately, because of they had their patent, other people could not really get into this field. To industries were not willing to go into it. But once in 2010 the patent was over, almost everywhere people started working in a big way on this field, and now you can see a lot of other companies have already started. For example, Kaneka, Sharp, all these things, and they have also started making very high efficiency cells by making back contact cells. Sharp has made 25% on this. Panasonic, again, Sanyo basically has changed to Panasonic, which is they also nearly 26%. And mainly the Kaneka, which has made a rapid improvement in the cell efficiency. they went up to 26.7%. That's a record now. However, you have to remember that back contact cells are difficult to make because you have all the N and P layers on the backside. So the making this with any sorts of lithography or masking is a very tough business. So industrially, still it's tough to make back contact cells. I just told you, just because the patent of Sanyo on heat cell was getting over, Europeans also woke up from that time. They woke up from this and they wanted to start this heterojunction cells. Europe, the maximum efficiency previously was only 13% efficiency. In my lab, it was 13%. Also, many other places around that only. So 2008, actually, the project started, what's called the Icee project. You can see here, there are so many companies involved and the institutes and companies involved. They made a big effort to catch up to Sanyo. And we all together, that time Utrecht University also was part of it, and our lab was part of it. And the efficiency was obtained around 21% within that project in 2011. It has said then after that getting up to make high efficiency cells. But that's how Europe took some time to catch up. Let me tell what is the advantage of silicon heterojunction cells. It's an excellent passivation of the crystalline silicon wafer surface. That is the most important thing. And there's one more thing is that there's a spatial separation of the recombination active metal contact from the emitter layer. So the metal contact is not in contact with the emitter layer. Then that leads to high VOC. You can also make smart designs. For example, you make lower process temperature. That means less warping effects take place. So you can make very thin cells, and symmetric cell structure can be made because it's a symmetric cell structure. Both the emitter side and the back surface side basically have similar type of depositions. So it's a symmetric cell structure that gives less warping again. And so very thin wafers can be made. And Sanyo actually had shown less than 1 micrometer cells with nearly 24% efficiency. There's one more advantage is that the conventional silicon, crystalline silicon, they have a very high temperature coefficient of efficiency. As you can see here, it's almost 0.45% efficiency per centigrade. So that means in a warm country, the homojunction cells, the conventional cells, are not good actually because you may get 3 to 4% less efficiency compared to what the rated efficiency, which is around 25% temperature, which is standard temperature. Whereas in India, for example, the cells modules can be up to 80 degrees when they are in the field. So nearly 3 to 4% efficiency will come down. Whereas the heterojunction cells have a very small coefficient. It's only almost half of it. So you will actually efficiency will be higher in a heterojunction cells compared to a homojunction cell. So even in the when you are using various types of emitter side oxide layer, if you use silicon oxide, you can still reduce the temperature coefficient almost to 0.1% per centigrade. So there's hardly any change of the efficiency compared to the rated efficiency of the module. That's the one thing. As you see here, the left side of this slide shows you what's the future of the predictions of the future. That's why the ITRPV, which 2019 is predicted this one. So now actually BSF, aluminum BSF solar cells modules are in the market maximum, and they will be there for some time. However, already you can see here the PERC cells of Pearl or PERC cells, the PERC type of cells are now coming up. And so by 2016, there won't be any more aluminum BSF cells, mostly the PERC cells. However, you can see here, slowly the silicon heterojunction is trying to catch up the market. And by 2026 or 2029, there will be quite a big market for the silicon heterojunctions. But Part cell probably is going to dominate for some time to come. And then you have after that you have IBC, that back contact cells will come into picture. However, that will be very industrially very difficult to make, and so it all depends on the future how it will come up. I see here in the right hand side also. See, aluminum BSF mostly it will be around maximum that can be reached is around 20% efficiency. Whereas PERC cells, the next generation will be PERC cells going to dominate. It will be around 23.5% efficiency will be achieved. And then the passive contact cells will come. That means silicon heterojunction cells or TOPCon, whichever tells. They will be 25% around. Then the back contact cells of passivating back contact cells will come, that are around 26%. Then the tandem will come after that. So they'll come to market. So tandem also is one of the future prospect for using silicon heterojunction cells. So that's why a lot of people have already been busy with making tandem cells, doing silicon heterojunction cells. Especially Oxford PV is very much interested in this. And you can see the very various places from the EPFL and Helmholtz Centrum and PVCom, Oxford PV, all these things, you can see they are around 26% efficiency can be reached, which is not higher compared to what is already a record in the baseline silicon, the silicon heterojunction cell. But it is very near, much nearer, and the prospect is that one can go up to 40% efficiency. Theoretically, 40% efficiency is possible. Above the Shockley-Queisser limit, it's possible to reach. And silicon, actually, Oxford PV showed claimed at least 28% efficiency for a silicon heterojunction cell. That needs to be a bit more confirmation from other people, but they claim they have 28% efficiency, which is higher than the silicon heterojunction cells, single junction cells. So it's already crossing that one, but I still have not crossed the Shockley-Queisser limit. Why this efficiency matters? Because the efficiency is the higher the efficiency, the balance of system cost will be reduced. As you can see here, left side the projection of the balance of system. The balance of system almost is a big part of the module efficiency, the levelized cost of the electricity. So one has to keep the balance of system cost low, and so efficiency matters. You can see here the Oxford PV showed on chart that if you make a increase efficiency, cost will reduce by 17%. So the efficiency of the price of that will be mostly because of balance of system cost, because you have less area used and other costs of wiring, other costs will be reduced. One more thing is important to know that the 26.7% efficiency that is made by Kaneka is almost reaching the Shockley-Queisser limit. So what else can we do? The main thing here is that you cannot increase the efficiency much from single junction. What is necessary is that to reduce the cost by many methods. To change the fabrication process. At present, mostly the silicon heterojunction cells, like homojunctions also, are made in the batch type process. For example, you can see here, just like here I have shown you a multi-chamber system in which you can take this is our raster system in my lab. So you can start putting your software here, and this robot arm can take to P-type layer, I-type layer, and so let's say you have an N-type silicon, you go to intrinsic chamber, one intrinsic layer, then P chamber, P layer, and you reverse, you flip it, and go to again the intrinsic chamber for the passivation layer, and the N chamber for the N layer, like that. So these are a batch type process, and that takes long time. So industry also mostly uses a batch type process, that due to which the throughput is reduced. And also there are other aspect problems, for example, like dust formation, and you have to clean the system regularly, and there are multi-chambers, so all these chambers have to be cleaned regularly, and that gives yield problem, also throughput problem. That actually increases the cost of production. So this I show you schematic of the silicon heterogeneous cells typically. So I say that you take a textured silicon, you take silicon 100 wafer. If you put it into etching agent, you get a textured surface with 111 facing surface, on top of which you have the intrinsic layer of 4 nanometer. Then you have let's say around 4 nanometer, and amorphous silicon, let's say around 10 nanometer. Then ITO is around 80 nanometer. Then the metal contact. Backside again, you can also similarly, you have intrinsic layer of 4 nanometer. Again, N-type amorphous silicon, which is N plus amorphous silicon, which is basically aluminum. That's a BSF layer, back surface field layer. And there is a ITO, and then there is a metal contact. So the whole idea is to change the batch type processing to a inline processing, which is the substrate is moving. Why I am saying this one is that it's difficult to optimize the materials directly in a dynamic moving substrate system. Most of the optimization processes are done in the batch type processing, because there you can understand all the parameters easily, the process parameters, and you can tune the parameters. Whereas in a dynamic system where the substrate is moving, it's difficult to change the parameter space. So here I can show you if the processing is changed to the dynamic system. Here, let's say there is this a plasma zone, and the substrate is basically moving here. If you keep the substrate here as it is, stuck it here, it's a stationary wafer, but normally it should be moving from one side to another side. While the plasma zone, the silicon layer is the silicon radicals are formed, and they will deposit on the surface of the wafer. So it's moving on the top of the plasma, and the plasma is made from the silent gas. Typically, it's at the plasma CVD processes, which is by around 13.56 megahertz. But we work on the very high frequency plasma, 60 megahertz. So one more benefit is that you can make very thin wafers, which can be flexible, and they can be on the dynamics. You can have a dynamic depositions on the flexible substrate. So the substrate goes on a web and goes from one side to another side. So what's the benefit in this one? Here it's a continuous movement of substrate. So the throughput can be increased depending on the bed speed. And also one more thing, there is a very little chance of the dust formation. I'm not going details into that, why dust formation will be reduced, but as the gas is continuously flushed here, there is a very little chance of dust formation. So that will increase the yield. One of the major issue, or rather the main point where one looks at the silicon heterojunction cell is the crystalline silicon amorphous interface. If that is good, then you get a good efficiency. That's you get good efficiency. So that's basically achieved in a silicon heterojunction cells. So here, for example, I show you in the left side a typically silicon surface on top of which amorphous silicon is there. If you make this one, you can get almost up to 10 milliseconds, more than 10 milliseconds you can get of the lifetime. And this is you have to make in a typical amorphous silicon deposition range, where you can get this one. If you slightly go away from the optimum value or the good value of the process parameters, then you will get into what's called the epitaxy. And epitaxy is not a good thing. So the silicon should not. It's easy for amorphous silicon. It's easy for the silicon to grow as crystalline silicon on top of crystalline silicon. as the bottom surface, the wafer behaves like a seed layer. So it's always a chance of some crystallinity forms on top of this wafer before the amorphous silicon comes in. That actually kills the cell. So the interface between the crystalline silicon and amorphous silicon should be very sharp and clean. And that only you can get more than 1 millisecond. You can go up to more than 10 milliseconds, as you show here. This one. Whereas if you look at the right hand side here, it is made slightly high power, the amorphous silicon plasma power. So here you can start seeing there is some crystalline silicon growing on top of silicon wafer. They grow conically here. They are not everywhere. Even a small one forms here. It already kills the cell. I can see there the lifetime has decreased to 0.24 milliseconds. So one has to be very careful on making this amorphous silicon on top of crystalline silicon. Now, where is the issue then here? So this is basically has been shown this the incubation phase of amorphous silicon before crystalline silicon cell is well known. So the in a typically amorphous silicon made on top of crystalline silicon for the heterogeneous cells, it's made at a protocrystalline condition. That means because they are made at low temperature, around 120 degree or something like that. So the amorphous silicon basically has to be a good one. But low temperature is made because we want a lot of hydrogen in the material. So they are made at low temperature. However, if you make at low temperature, material is very bad. So it has to be made on a high hydrogen dilution condition. That means lot of hydrogen to silane ratio has to be made to make a good layer. That's called a protocrystalline condition. In this protocrystalline condition, actually, there is the material grows as amorphous silicon. After some thicknesses, they become crystalline silicon. So whole idea is that to stay within this amorphous silicon before it becomes crystalline silicon. So we make amorphous silicon in a protocrystalline condition, but thickness is such that it remains amorphous silicon before it becomes crystalline silicon. Now the problem comes in the why this amorphous silicon incubation phase is made why it comes because of what's called initial transient plasma. Let's say here I'll show you. This is called this is in the 10 seconds range of the from the starting of the plasma. You strike the plasma, you apply a power. Within 10 seconds, this sort of thing will happen. What happens is that in the let's say this is your plasma, the electrode area, and this is a chamber wall. So it's a big chamber here. This is I'm showing on the right hand side of the chamber. So this is your cathode area. Cathode is anode. The substrate is connected to the anode. Is attached to the anode, and here basically silane gas is coming from one side and going to the other side, or silane coming from the silane hydrogen coming from the cathode in the here, and then the gas is going out to the chamber wall, and there is a pump here. So what happens that once you put the gas, the silane immediately depletes. So from here, so then what happens that the silane from the background in this region, they back diffuse to here. Because of that, there's a lot of silane comes here, and this goes on for some time before it reaches a equilibrium, and in which there is no more silane back diffusion from the background gas to here, and that's called the initial transient plasma. This due to which initially there will be amorphous silicon, and before they reach a equilibrium phase, in which there will be crystalline silicon. And that's why the amorphous silicon is formed. Now, in a batch type process, this is what normally one sees, and this is a batch type. In an inline process, the gas is already discharged. Then the substrate is coming. So this initial transient plasma doesn't come into picture. So what will happen is that in an inline process, if you take the same process parameter from the batch type process and put in the inline process, you start as crystalline silicon because there is no incubation phase. So incubation phase is amorphous silicon, whereas in an inline process, the incubation phase is very small or not there. It's not there. So that means it will start as crystalline silicon. So taking the process parameter from batch type process directly to the inline. So that will be bad for solar cell. So this is what actually we had done a modeling, which shows that how the initial transient plasma is seen. And this is basically transient region, and this is basically amorphous region. And whereas this is typical in a batch type process of how the silent gas from the chamber basically reaches equilibrium. Whereas in an inline process, this transient system doesn't exist. So they'll come as crystalline silicon directly. If you use in a okay, so what we did is that we tried to find out a deposition conditions in which there is no transient plasma but remains amorphous silicon. So that can be done. Let's say here you can see here. If you take a typical this red one, a typical condition from the batch day process in which there is a transient plasma. If you take this one and do it on amorphous on the inline process, that becomes crystalline. As you can see here, there is a difference in the crystallinity in a thick. You can see there's crystallinity compared to crystalline silicon from the stationary one. So one of the ways to mitigate this one is to increase the total flow of the gas. This is R means dilution, that means hydrogen to silent ratio, and this is power. So if you increase simply total flow, you can see then so this becomes the initial transient plasma is gone. So basically going to amorphous silicon, it doesn't go into crystalline silicon. And you can still improvise on that. You see here R14, this hydrogen to silent ratio 14, and low power, and the flow of 101, 107. You can get nicely, very nicely without transient plasma. So this basically gives you. This is the condition in which you could do this one in amorphous in a stationary as well as in the dynamic depositions. Similar type of transient plasma will come, and so that this condition can be. You can move to you can transfer from the stationary to dynamic deposition. That's what we did.
Professor Rat, the 30 minutes are over. Just a fire.
Yeah. Okay. I just want to just go ahead. This one, just continue on that. So we did that one, and we got nicely the interface between the amorphous silicon and crystalline silicon in a dynamic depositions, and. So the whole idea is that in conditions of no depletion, transient resulted in excellent passivation, and these conditions you can transfer from the dynamic to from the batch day process to inline process. So we got maximum lifetime of 6 milliseconds by this, and implied VOH of 716 volt. So from in IIT Madras, DST has given a project, a 40 crore project, in which we are making silicon heterojunction cells and tandem cells. Within that, we are working along with the BHL to transfer the technology of the inline processing. And so the BHL has made an inline processing tool in which log there is a isolation chamber, interesting chamber, P chamber, N chamber, ITO, and ECD clock. So there we are trying to transfer the technology, and this is what the BHL plant looks like. So conclusion is the batch type to inline tool process transfer can be made with appropriate condition. Initial transient plasma is the most important parameter to be controlled. Thank you.
Thank you, Professor Rat. I think we have time for one very quick question, if there is any. Actually, I had a question. Can you comment on the need for the 60 megahertz plasma?
Yeah, 60 megahertz plasma is the high frequency plasma. It's good because the ion bombardment is reduced, because the high frequency, the ion energies are much reduced. That's a big effect on the passivation quality. The second thing is that not so important for heterojunction cells is that the deposition rate can be high, but mainly it's the ion bombardment is reduced considerably, and you can get, of course, in the standard PCVD also you can do that by using high power, high pressure condition, but then you start getting powder. Whereas in a very high frequency plasma, 60 megahertz or something like that. So you can get a pretty nice low ion energy bombardment without any powder formation in the plasma.
Well, thank you. If I don't see any other questions, so let's thank Professor Rath. Thank you for a very interesting talk.
Thank you.
And next, I would like to invite Shabal. Professor Shabal Sarkar completed his PhD from Weizmann Institute. Yeah, Shabal.
Yeah, thanks, Sushman. Please allow me to share my screen.
I think you should have the ability to do so. Do you see a link in the bottom which is share content?
No, the share contents is basically, it's not there. You have to enable that.
No, Professor, you can do the bottom share after the video.
Yeah, it is there, but
It's disabled for him for some reason.
yeah.
Is it possible for you to look? I mean, is it a question of the link? Is there a common link or there was a special link for the speakers?
I think it is a common link, right?
I mean, I see the share link option, and I'm not a presenter.
I can send you. I can send the link if you want.
Okay, can you send it on this chats? Okay.
Okay.
Okay, while we wait, let me just quickly introduce Shabal. So Shabal completed his PhD from Weizmann Institute of Science in Israel in the year 2005. After postdoctoral research work in Missouri University of Science and Technology and subsequently University of Colorado at Boulder, he joined IIT Bombay in the year 2009. His current research interest is in flexible Ross-kind devices and its reliability. His group is active in developing newer chemistry for atomic layer deposition for photovoltaic applications. In this talk, Shabal is going to talk about, the title of his talk is Stability Enhancement for Active Interfacial Engineering and Hybrid Perovskite Solutions. So Shabal, the floor is yours if you see the link.
Just use the link.
I see a raised hand from ICW 2020. I'm assuming this is the IT team. Do they want to add anything? Okay.
It is by mistake from very long. It is there.
I see.
Is my screen visible?
Not yet, but there are two of you. So there's an echo. If you could log off from the. Uh,
It is written that we cannot display your shared content. Make sure that you have allowed permission to share content, and then please try again.
Any ideas?
Host Icee, someone who is handling this Icee.
Hello. Yes.
Can you allow the content from Professor Sarkar?
Actually, sir, I have no video, so can I? So what I shared.
Okay. Sorry, Professor Sarkar, if you don't mind, if you can send quickly so that I can share it. So
Sure,
without
sure,
any
sure, 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 sure.
the file is not big, please send to me. OMC at IIT.
Is it possible to then first finish the other speaker? Because
Yeah,
it
please
might
go
take
ahead.
5. Yeah, okay. All right. So in that case, let me actually invite our fourth speaker, Ms. Avriti Srivastav. I hope I have not butchered your name. The title of her presentation is Micro Inverted Pyramid Based Silicon Surface by Copper Assisted Etching for Effective Light Harvesting and Solar Cell Applications. Avriti, are you here? And if you can share your screen, you're welcome to present. Avriti, could you hear?
No, no.
She was here. I saw her. Okay, disconnect.
Oh. Yeah, she is now disappeared.
Shabal, you have sent the presentation to Vamsi or to me? Shabal, can you hear me?
Yeah, I can.
So you sent the presentation to me or to Vamsi?
Yeah, I just sent it to you.
To me, which email address, if you don't mind, because I have not received it on my main one.
Sure. Yeah, I see.
Found it. Yeah, got it. Thank you. All right, let's get started. Is the screen visible?
Yeah.
Everyone? All right.
Yeah, exactly. So Shobhan, the way I will do it, I will ask you to, the click next and click next.
Yeah, absolutely.
Okay.
Yeah.
Shall I?
Yeah, please. The stage is yours.
So, good afternoon, all. This is Shabal from IIT Bombay, Shabal Sarkar. first of all, please apologies for all this technical inconvenience that is that you had experienced and that I also had experienced. Firstly, I would like to thank the organizers, thank to Vamsi and Shushovan for organizing this conference. Okay, in today's presentations, that what I will be talking, and I consider this kind of a little bit elaborated presentation. So I would like to go a little bit slow. So what I will be talking about today is that, as the title does suggest, I will be talking about at ALD of alumina on perovskite solar cells. Okay, at the first part, and in the second part, next please. And the second part, I will talk about the role of active interfacial engineering. Now, as you can see, these two particular parts, okay, the alumina and the interfacial engineering, okay, it in principle, and just from the from if seeing from the 30,000 feet above, it doesn't look like that these are kind of a mixing or gelling together, because alumina is alumina. It's an insulator. It has nothing to do with the interfacial engineering, hopefully, but it does. And in this whole presentations, my motivation is to show you that how the alumina is basically playing a very nice interfacial engineering role on interfacial engineering. Next, please. So let's begin. Okay, next, please. Okay, so let's begin. So why particularly I will be talking, or I'm interested in talking about alumina? This is actually based on certain series of publications that has been coming in last kind of a 2 to 3 years. Okay, so in this particular presentation, next, Shushwan, please. Okay, and keep on doing a little bit. Yeah, in this there is a series of publications. That publication shows that by somehow alumina is playing, and particularly alumina, when I'm talking about the alumina, I'm talking about the ALD alumina. This is no other deposition technique, as for an example. So here in this series of publications, and I'm citing some of them, there are plenty many, I may be missing something. Okay, but in the whole set of publication, what I'm seeing is that alumina plays a kind of a role, or a kind of a magic role, quote unquote, which essentially improves the perovskite's stability. Now, that perovskite has a problem of its stability. There is two types of stability: intrinsic stability and extrinsic stability. Now, since I'm talking about an alumina as such, so it makes you giving you a kind of a perceptions that it is basically covering up the device, right? So if I'm talking about the covering of the device, for an example, I'm talking about the protecting or stability as far the extrinsic stability is what is extrinsic stability is concerned. That means stability against moisture, stability against water, okay, and actually basically mostly these two. So in terms of extrinsic stability, I'm basically giving you the whole, what we have seen during, while depositing with the alumina. Now, when I'm talking about the extrinsic stability, please next, please. So in talking about the extrinsic stability, I started making a standard device. Now, a standard device is having, as it is showing, and I'm thankful to as Shushovan is showing, that the standard device is made of the SNO2 device. Now, I'm not talking about the titanium dioxide device, only because of the fact that because titanium dioxide devices are having a more hysteretic, it's more hysteretic, and therefore the stability due to the instability due to the hysteresis always comes into the play, which is the major effect than that of the extrinsic stability. So what I'm talking about the tin oxide based devices. Now in a tin oxide based devices, you have the perovskite layer, spirometad as a whole transport material, and the gold electrode. We illuminate from the bottom, and then you generate an electron on hole pair. Okay, and then basically you do a connections from the top cathode and the bottom and the bottom electrode, and you make the devices. Next, please. Next. So the whole device which has been shown on your left, and in order to carry forward, I am making another schematic which is shown in your right. Okay, this device is essentially a kind of a same thing which is been given on your previously on your left, and having a cross-sectional ACM which is shown on your left. Now, this particular devices is at an average efficiency of 19.2 to 20.3, 20.4, around this much percent efficiency. Now, always batch to batch, it varies. Okay, but strictly speaking, we are talking about the high efficiency device, because when you are going to the low efficiency device, something like 15, 16% devices, those devices have already, they have many other issues, so they can contribute to its instability. So in order to remove those particular factor away, we are talking about those devices which are basically high efficiency devices. And in these particular devices, the another main factor is that apart from the SNO2, we use that doped spiro. Okay, so often people may use doped spiro, may not use doped spiro, but here we are typically using the doped spiro as a whole transport material. So let me take you the right hand side schematic and let's talk about that how and where this alumina can be deposited. Next, please. So let us look at this schematic device. This schematic. Now the alumina can be deposited and many other places, because you know there are a lot of junctions: FTO, SNO2, perovskite, spiro, gold. There are a lot of materials are there, so you can, in principle, you can put it alumina, any of the places. But anything below the perovskite, it doesn't make any sense, because there you have nothing to do with the extrinsic stability, unless and until we are missing something. So when I'm talking about the extrinsic stability, I'm talking about the putting protecting the perovskite from the top. So if I do these things, I try to do it with the alumina, and this alumina is deposited with the simple TMA water chemistry. Now TMA is a trimethyl aluminum, and water is water, and basically over here we are talking about the okay, so let me put it in this way. The deposition temperature is around 70 to 80 degrees centigrade. Mostly we have done it at 80 degrees centigrade, and the cycle is 130, 130. That means I have a 1 second pulse of the TMA, then you have the 30 seconds, purging, 1 cycle water, and 30-second purging. Now the question can arise, instead of a water, why not you use the ozone? It also possible, but as of now, for just let's not take parameterize everything as at one time. Let us parameterize only one particular point, that is the simple using this simple TMA water chemistry in these particular devices. So how? So now let us question arises. So where I have to deposit? The first possibility is that I can deposit this alumina layer on top of the spiro, and I can please next please, and on top of the alumina, I can deposit the gold electrode. Okay, so this is the possibility one. The next possibility is that I can deposit the alumina on top of the perovskite, and on top of the alumina, I can deposit the spiro, and then I can deposit the gold. Or in the third possibility, I can have the whole stack of the device, and I can deposit the alumina on top of it. Now, yes. Now the question arises: why should I have all these three possibilities, and which possibility is basically scientifically important and technologically important? So I divided all these things as a scenario one. Next is the scenario two, and the third is the scenario three. Now I would try to come with each and every scenario at one particular time. So let us take the scenario one. And in the scenario one, what I have deposited, I deposited alumina on top of the spiro and gold. So when I'm talking about the depositing of alumina on top of the spiro, okay, so what you do, you basically you take the you take the device stack without the gold, you put it in the ALD reactor, you deposited the TMA water chemistry, and then you deposited the gold, and you measure the simple IV characteristics. Next, please. So now when you make the IV characteristics, next, please. Next, please. No, yeah. So when you measure the IV characteristics, as you can see, that your IV characteristic is disastrous. Okay. Now, when I'm talking about the one thing I would like to make a point over here, that whenever I'm talking about this much thick nanometer of alumina, Now, essentially, this is a kind of a back calculations. That means instead of putting it on top of the spiro, as if I'm putting it on top of a silicon and I'm measuring it. Okay, so this nanometer of thickness essentially doesn't give you any sense. It is better to say that if I'm talking about the, let's say, 10 nanometer, it means approximately 100 cycles of TMA water. Now, whatever it is, this is a very important. First of all, this is very important to understand, because whenever I see in most of the cases, we can see that the people are using those nanometer as in a kind these values, kind of a very loosely, I would say. Okay, so as you can see, the IV is a disastrous, and what we can see that this alumina layer on top of the spiro is basically making a kind of a barrier layer, which is obvious. Okay, and therefore the whole tunneling, transport is basically limited, and you can get you can get a bad device. Okay, which is a kind of a quote unquote non-working devices. So this is the scenario one. Let us go to the scenario two. Now, in a scenario two, what I have deposited alumina on top of the perovskites. Now, when I'm talking about the deposited on top of the perovskites, you have to be very careful, because alumina deposition is a kind of ALD, which is a surface limited depositions. And perovskite, you need to know that perovskite is a very sensitive material altogether. Next, please. So essentially, you are basically depositing a TMA water chemistry. Please, next, please, next, please. Yeah. So essentially, you're basically depositing a TMA water chemistry on top of a very sensitive perovskite layer at 80 degrees centigrade. And you have to remember two things over here. A, that often I see, not only you can also see that people are talking about the ultra thin layer by ALD. So in the ultra thin, people are talking about the sub nanometer or sometimes like a 1 nanometer of layer. Now you have to be very careful about it. Okay. Now when you're talking about this kind of a high roughness substrate like a perovskite, spin coated perovskites, okay, and I'm considering spin coated perovskite as a high roughness substrate in comparison to the silicon, by the way. Okay, so when you're talking about the high roughness surfaces, you have all those knees and bends and all those things. So the exact 1 nanometer conformality is difficult to achieve. I'm not saying it is impossible, but I'm saying with a good respect that I'm saying it's a difficult to achieve. So if you think about that, you're depositing a less than a nanometer or something like that, you can end up with basically depositing some cluster somewhere or the others. Okay, and may not be a conformal, or essentially not be a conformal. Second thing is that when you're talking about the depositions, it is a kind of a chemical reactions. Now, when these chemical reactions are happening, okay, you have to be very careful that TMA and water both can be harmful to the perovskite surface. Next, please. Okay, and in this particular sections, I will be presenting that how this deposition chemistry occurs. Now, first of all, as a student, when you are talking about that, whether your TMA water chemistry is working on top of the perovskite, what do? You take a perovskite, you deposit a perovskite layer. And by the way, when I'm talking about the perovskite, it can be it can be mappy, it can be multi-cation. Okay, so but doesn't matter as of now. Okay, and when it matters, I will tell you. But because I will be comparing apple to apples only case of the electrical characterizations. Now let us consider you are taking a mappy. Okay, and on top of a mappy, what you do, you deposit a TMA water of some 100 cycles. What you do your XRD, you do your XC2 FTIR, and what you see that, okay, fine, after depositing hundreds and some few tenths of nanometer, some few tenths, and it necessarily not be anything, some few tenths of nanometers of alumina. Okay, neither your XRD shows the lead iodide peak, neither you have a distorted FTIR. So basically, you as a student, you will feel very happy, and you can see that, okay, fine, when I deposited alumina, the grass is green and the sky is blue as usual. But when you go to the back to the basics, okay, please, next, please. Okay, when you go to the back to the basics, what you do, you started doing that quartz crystal microbalance. Now, this is a quartz crystal microbalance in situ. So in the quartz crystal microbalance, what you do, you deposit a thin layer of MAPI and trying to see that what is happening when trimethyl alumina and water is coming, simultaneously one by other. So what you can see from over here, you can see from the, if you can see my cursor, I do not know whether you can see my cursor or not. Okay, but if you look at the left figure and the first pulse of the TMA, okay, it's okay, the first pulse of the TMA, okay, you can see there's a mass decrease, and after that you can see there's a mass increase. So what this means, what this means, the first pulse of the TMA is reducing sometimes it started deposit after the first pulse is basically etching, and then it is started having a nucleation period, and then off now. Okay, now look at the first. You see the first pulse of TMA, it is going to the mass decrease, and the second figure on your right, which is supposedly to be the middle figure, okay, you can see there is a continuous mass decrease if you continuously pulse the TMA. What does it mean? It means that it doesn't form a self-assembled monolayer. Basically, it is etching the system. It is etching the perovskite. It removing the, removing the methylamine altogether. However, on top, next please. When you do the water, you cannot see there's no change as such. Okay. So what is important to know, that TMA is etching, however, the water doesn't have anything. So therefore, whether you choose water or ozone, it doesn't make any difference whatsoever, neither material formations nor electronic way, to be noted. Now, if you look at the TMA now, as we can see that the TMA is etching. So next please. Next. Yeah. So as you can see, so we started looking at the in situ mass spec. Okay, and then we do the certain DFT, which essentially shows us that as the TMA is reacting with the perovskite layer, taking the methylamine out and leaving you the lead iodide at the top surface. Next, please. So now next, please. Next click. Yeah. Next click, please. So let me get the whole screen. No, yeah. Okay, fine. So essentially what you can build a TMA water layer on top of the perovskite. However, you should have and you must have a lead iodide interfacial layer. Now, whether this lead iodide interfacial layer is good or bad, we are not very sure. There are certain reports which says that lead iodide at the interface, enhances the stability and so on and so forth. But at this moment, I do not wanted to comment on that, because this way we can be diverting. But essentially, what you can see, that you have a lead iodide at the interface. Now, if you make the devices with the lead iodide interface with an alumina layer, our devices doesn't work at all. Okay, so which ends up to a situation that in the scheme 2, where you deposit the alumina on top of the perovskite, you essentially, your device doesn't work, or our devices doesn't work. Now there are certain reports which says that there are devices who works, but to be honest, our devices doesn't work, which funnels down to the next slide, which is the scheme 3. In a scenario 3, what we have done, we deposited the alumina on top of the whole device stack. Now, whole device stack, which includes the gold electrode. Now, when you are depositing a material on top of an inorganic and organic layer with an ALD, there is a possibility that your organic layer has, which is a kind of a little bit acts as a kind of a, next please. Next. Yeah, that's it. So that's it. So your organic layer, which can act as a sponge, so essentially your material is not only limited to the depositions on the top surface, but it is the deposition happens in the bulk and it moves to the top surface. Okay, it is just like a kind of a tree type of things with a lot of things, what do you call that? It's a kind of a tree type of thing. And then alumina is basically deposited on also on the bulk of the substrate, which is schematically shown over here. The difference between the inorganic substrate, the TMA water deposition in the inorganic substrate, and TMA water deposition on an organic substrate. Now, since we know this, so therefore, what you can see, let us go to the again to try to see what the QCM tells us. Please, next, please. Okay, just give the whole slide. Okay, fantastic. So when I see the QCM, I essentially see two basic differences. The two basic scenario. Scenario one is that at the linear growth regime, which is approximately, let's say, 1,000 second, 1,000 second plus, where you can see that your growth is basically essentially linear. In that particular case, your growth, whether it is on the whether its substrate is organic or inorganic, doesn't matter, because in that case, what will happen? You're depositing an uniform deposition, that is mass gain per cycle is basically uniform. Now, at the initial surface where you are talking about that whether it is depositing on an organic substrate, what you see a substantially high mass increase, and which again goes down and then is basically flattened as if it is the deposition is on the inorganic substrate. Now let me since in an absence of my cursor which has been working, which is not working over here, okay, in an essence, let me explain you over here, and which is very important for you to understand. Now look at the figure on the right side, the red and the black. What you see over here is the red card shows that the mass changes per cycle when the alumina is deposited on gold. What you see, you can see your mass change is basically uniform, whether you're depositing 10 cycle or 100 cycle or 200 cycle, it doesn't matter. Your mass change is always uniform. That means the growth per cycle is always at constant. However, if you look at the black dots, which are connecting black dots, what you can see that at the initial stage, you have a essentially high mass gain, which again drops down, and then it becomes approximately similar to what the red one. Now, this increase in the mass gain and then the decrease, what it essentially shows us, which is depicting that there is during the initial fast 20 cycle, that there is a considerably high growth in the material. Now, in the material, I would say not on the material, because this mass change is happening. The growth started from the bulk, so it is inside the bulk, and then it is basically popping up, and then it is basically flattening up, and then the red and the black basically stay. Now, next, please. So, which shows us that alumina is growing on the spiral. It is coming from the bottom of the from the bulk of the spiral, and then it pops up and it covers the your top surface, which is essentially needed for the for the what do you call for acts as a kind of an encapsulation. Now, when I'm talking about the encapsulations, because this alumina pops up and encapsulate the whole surface, which is basically schematically shown over here, that means the whole your device stack is basically encapsulated by that green stack. Now you started measuring. Okay, now your electrical measurement started. Now what you see, that you started measuring electrical measurement, that what you do, you put the light on, and you started measuring IV, and so on and so forth. That means each dots are individual measurement, not a continuous measurement. Now, this is very important to say. And when I say the individual measurement, that means between a measurement N and the measurement N+1, there's a difference that the device relaxed electronically, not optically. So when you do this kind of measurement, what you can see, whether this is encapsulated or non-encapsulated, that means whether it's a ALD alumina is there or not there, it is essentially stable. Okay. And for one particular, for the pristine devices, I'm showing for 24 hours. And for the alumina coated devices, I'm showing for the 140 hours. and the only the difference, please note down the difference. This is not the same. Okay, so please note down the difference. So, but what it says, that essentially both are behaving similar way. But that is not the stability measurement what you're talking about. Stability measurement considerably comes from here when you do the measurement in a continuous. That means you are continuously measuring the current. Now, the drastic difference between your right-hand side graph and your left-hand side graph, which is the pristine graph and the LD coated graph, it says that in the pristine devices, the current density goes down, 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 and after 8 hours is basically the cell is dead. While as for the alumina coated devices, even after 140 hours, it is a rock solid, rock stable. Okay. Now, even if you can think about that, I'm probably a little bit, exaggerating as a rock stable, but trust me, it is very stable. Now, this is under ambient conditions. What you do when you deposit, next please, when you do it under nitrogen condition. Under nitrogen conditions, okay, the alumina coated devices, again, it's a very stable, while in a pristine devices it is started decaying, and after 8 hours it is kind of behaving something like 50-55% of the initial devices. But the drastic difference comes over here when you do it under oxygen. When you do it under oxygen, what you can see that your device doesn't exist even for an hour. However, in case of a alumina coated devices, again for 140 hours there is a stability. However, it is there is a certain subtle decrease at the beginning, but over the time, okay, it is very much stable. What it signifies? It signifies a simple thing, okay, that we know that oxygen basically decays, that is detrimental for the stability of the perovskite devices. In case of am I out of time?
Yeah. Can you please try wrapping up quickly?
Sure. Okay. So it is. So it is, sorry for that. Give me 2 minutes. Okay. So now, when you, even in the oxygen, it is stable. So that means the alumina is essentially encapsulating. Now, when you're talking about the encapsulating, I'm talking about something like around 10 nanometer or 8 nanometer of the devices of alumina, which is ultra thin. Okay. So can you go to the next, please? Okay. Now, when we do the such measurement over the hours, and what I'm showing you over 7,000 hours. 7,000 hours is essentially kind of a 300 days. In a 300 days, the alumina devices decrease approximately 16% to its initial values. Approximately 16%. So even if your your devices is your devices is still quote unquote stable, much more stable than that of a non-coated. Next, please. Next. I'm skipping this R. So what I okay, and can you go up, please? Sorry. So what you can see that the big major difference between all those IV over 7,000 hours, that means over the 300 days, and this is a kind of a kind of a considerable work. What you can see, the change is essentially it's in fill factor. Now, when you look at the fill factor, can you go to the next, please? Next. I would like to skip this one. I would like to skip this one. Yeah. So when you would like to see that what happened when you deposit the trimethyl alumina, and try to see previously what I skipped is the some in situ characterizations. So right now I skipped that one and just came back came to the electrical characterizations. So initially when you see the TMA and water when it is deposited, next please. Next please. The resistivity of the spiro is essentially changing, and these changes is not because of the trimethyl alumina, but only because of the water which has been shown over here. Now, what water does, in the at high temperature, and at when I'm talking about 80 degrees centigrade, perovskite, this pyro is getting with the water, it is getting furthermore, so-called quote unquote dope. And because essentially, next please, next. So when, yeah, thanks. So when it is perovskite is getting dope, its conductivity has improved. Okay, so eventually you do not need a TMA water, but you essentially you needed water. What happened when you are doping the perovskite? When you are I'm sorry, excuse me. When you're doping the spiro, your conductivity has changed. Next, please. Next, please. Next. Yeah, over here. Next. Well, that's it. Okay, and you're changing your conductivity. So what you can change, if you're changing your conductivity, then your ion accumulations at the perovskite spiro interface, which is changing. Now, what I'm showing you on the left two characteristics is the one on the left is the alumina coated devices, on the middle are the pristine devices, and on the right, okay, what I am showing, I take the IV characteristics at each and every point after 30 seconds or something like that, after 30 minutes, or in a periodic manner. Okay, what you can see that as soon as you started, and at the time, at the beginning, you get a IV characteristics which is given in the black on the I'm talking of the graph on the right, the black one, okay, which shows a nice characteristics. And when you started measuring it under continuously under a pristine, what you can see started a kind of a S type of characteristics. Now this S type of characteristics happens only when there's a double diode type of characteristics essentially. Now, as soon as this double diode characteristics is coming into the play, the whole devices started going bad. If the double diode characteristics, that means because of the ion accumulation, if there is a no barrier layer, additional barrier layer, the system doesn't go bad. Now, since I do not have the time, so I'm not going to the rest of the device physics studies and the device stability studies, but essentially I would like to go to the conclusion, if it is okay with with yeah. Okay, so what we see that in case of a perovskite devices, your interface starts going bad fast, then your material goes bad. So please don't blame the material. It is the interface which goes bad, and then the material goes bad. And if the interface is good, your material, it takes way more time to for device, the device stability will become better. Okay, with this, I would like to thank my next, please. Yeah, I would like to thank the students, okay, who has worked really hard on this, and their results are presented here. And I would like to thank, next please. Yeah, I would like to thank, okay, I would like to thank the funding from the MNRE and the Department of Science and Technology. Thank you very much. Thank you, Shushoban. I'm done.
Thank you. I don't think there's time for questions, so let me just move on to the next speaker. Rithi, I hope I am not murdering your name. If you're available, please come online. And the title of your presentation is Micro Inverted Pyramids Based Silicon Surface by Copper Assisted Etching for Effective Light Harvesting and Solar Cell Applications. Rithi? Hello.
Yes, I'm here.
Oh, yeah. Okay.
I tried
So
to
the
share
floor
my
is yours.
screen first.
Yes.
Okay, thank you. So are you able to see my screen share?
Yes. We are not in presentation mode, but yeah, good. Great.
Okay, thank you. So good afternoon, everyone. Myself, Avriti Shrivastava. Today's topic of discussion is micro-inverted pyramids-based silicon surface by copper-assisted etching for effective light harvesting and solar cell application. So these are the content which I'm going to discuss. Firstly, the working of solar PV cell, then losses associated with solar PV cell, why silicon nano or microstructuring, what happened when we perform that kind of nano or microstructuring with wet chemical etching or with dry chemical etching route, then focusing on copper assisted chemical etching, my experiment performed so far, then morphology, what is the mechanism behind the copper assisted etching, that is oxidation or reduction process, then inverted pyramid like structure, why we are getting that inverted pyramid like structure, then their reflectivity plots, particularly SWR, which is solar weighted reflectance required for solar cell application, then conclusions. So what happened when we expose that kind of devices? It basically based on photovoltaic effect. Firstly, the absorption of solar radiation takes place, then charge carrier generation and charge carrier transportation takes place. If the absorption is not efficient, then that kind of losses comes under optical losses. If the charge carrier generation or transportation is not efficient, then that comes under electrical or electronic losses. In optical losses, there is reflective shading and unabsorbed radiation. So conventionally, people were using anti-reflective coating, having refractive index in between air and silicon, which minimizes the reflective losses. But there are few limitations with those ARCs also, as they perform well for a limited spectral range and for a specific angle of incidence. So the possible solution for that, for replacing that ARCs is by nano or microstructuring of silicon. So what ultimately happens when the nano or microstructured silicon exposed to the sunlight, then what happened, those due to those nano or microstructure, the interaction area increases and the light getting trapped onto those structures. So the possible approach for getting those nano or microstructure is by wet chemical route. What happened in wet chemical etching? Firstly, the transportation of the reacting substrate towards the reacting surface, transportation of the reactant towards the reacting surface, then the reaction occurs there, and then uh, the byproduct away from the surface. That how it's work. And there are three type of etching comes under wet chemical etching. One is alkali etching, the second one is acid etching, and the third one is metal assisted chemical etching. If some for a desired nano or microstructure, for if some metal assists that kind of wet chemical etching, then it comes under metal assisted chemical etching. So as per literature, most of the studies have been done on the material like silver, gold, and platinum. So we found that yes, there is a research gap. Material used in MSE, it add up the cost, or nanomicrostructure enhances the surface recombination also. So our aim is to develop efficient and cost-effective nano or microstructuring of silicon for solar cell application. So we are moving towards copper-assisted chemical etching, which replaces the silver or gold-like costly metals. So how we perform copper-assisted chemical etching? If we start from SCAD solar grade silicon wafer, moving towards the standard cleaning procedure, and then copper-assisted etching. Once the etching is performed for a certain concentration of H-bath solution and for a certain time interval, then once that etching is done, then we remove the copper nanoparticle from the silicon substrate by ultrasonicated with concentrated nitric acid. These are the digital images of ASCAD silicon wafer and partial polished substrate. So why we perform the same with those kind of different surfaces? When we start from ASCAD silicon, what we found that ultimately what we are getting nanoporous structure mostly, even if we are able to achieve our desired structure, but there are a lot of surface defect in the starting ASCAD silicon wafer. So we try the same with completely polished surface, but as there are less defect center in the completely polished surface, so we are not getting structures, or what we found that even the reaction is not getting started in that case. So in partial polished, so we found that yes, we were going to perform some sort of etching for removing the surface damage, and we start with partial polished surface, then followed the same route, and we are getting uh, our desired structure. So what we optimize, that starting from damaged silicon solar grade wafer, we perform acid etching by HNA solution in 5:1:1 ratio, and then we perform copper assisted etching for a desired time and temperature in a particular H bath solution. And once that etching is done, then we remove the copper nanoparticle by ultrasonicated concentrated nitric acid. Through this schematic, I think the the experimental part is very clear. After that, what we are getting if we vary the molar concentration of copper. So what we found, if we vary the salt concentration, which is copper nitrate in our case, if we vary the salt concentration, we are getting nanoporous two inverted pyramid-like structure. So what is the role of that copper salt? If the salt concentration is high, then what happened? The H rate is very high because the deposition or dissolution is very high, So it increases or it enhances the H rate. If we vary the molar concentration of H2O2, so what we found that we are getting our desired structure, but if the concentration of H2O2 is high, then the desired one, then what happened? It moderates the reaction rate and the copper film is deposited onto the substrate. So what we found that yes, H2O2 plays a crucial role in this reaction. So we fix the concentration of the other H-bath composition material, and we vary the H2O2 with time. And what we found that we are getting inverted pyramid like structure in both the cases, but as you can see in case of SCAT, we are getting the inverted pyramid like structure in case of 0.70 molar concentration of H2 for 20 minutes, and in case of partial poly substrate, we are getting distributed inverted pyramid like structures, but in case of molar concentration of 0.60 molar for 15 minutes. So what we found that yes, in case of SCAT solar grade wafer, the reaction rate is high because there are a lot of defect centers. So the required H2O2 molar concentration is a bit high, but the desired time of etching increases. But on the other hand, in case of partial poly surface, as we have a smooth surface, so the desired molar concentration of H2O2 is a bit low, and so the desired concentration of molar concentration of H2O2 is a bit low, but for a some shorter time relatively than the SCAT solar grade wafer. So what we found that due to the large defects and centers, it allows the copper nanoparticle deposition, and the etching rate is relatively high. So we are getting nanomicrostructured silicon with defects in case of SCAT wafers. On the other hand, in partial poly substrate, we are getting distributed structures because there are less defect centers. So the nucleation or the deposition of copper nanoparticle is distributed in the partial poly substrate as shown in the schematic. So what happened basically here, the oxidation of silicon to silicon oxide and the deposition of copper nanoparticle from iron due to the reduction of iron to the copper nanoparticle. So basically what happened here, the copper nanoparticle drags electron from the silicon, the silicon gets oxidized to the silicon dioxide, which is then etched by the HF, which is already in the H-bath composition. So how we are getting that inverted pyramid like structure only starting from the silicon wafer, as the copper nanoparticle deposited on the substrate, it attracts electron from the silicon, gets oxidized into the silicon dioxide, then which is etched out by the HF. Then why particularly inverted pyramid like structure? Because due to the orientation of silicon 100, the etching rate of 100 plane towards the 100 plane and 11 plane is different. Not only the etching rate, but the deposition size of the copper nanoparticle is different in both the planes. In 100 plane, the deposited copper nanoparticle size is a bit larger than the 11 plane. So that's how the etching rate controls. Not only the orientation, the copper nanoparticle deposition, but the kinetic equilibrium of the copper nanoparticle deposition and dissolution plays a crucial role for that kind of inverted structure. So ultimately what we are getting, those faces with 1-1 alignment due to the silicon orientation itself, with that kind of inverted pyramid like structure having 54.7 degree angle in between them. So these are the reflectivity plot. We vary the concentration of H2O2 in both the cases. In case of SCAT silicon wafer or in case of partial poly surface, we ultimately calculate SWR, which is solar weighted reflectance. And what we are getting 11.88% minimum reflectance in case of S-cut wafer, or in case of 16.04% in case of partial polished surface. And then their relative time is there. We are getting minimum reflectance for 20 minutes in that case, and in 15 minutes in that case. So why we are getting 16.04%? Because we are getting distributed inverted pyramid like a structure. On the other hand, in conventional, we are getting 12 to 13% reflectance in conventional pyramid like structures. Or so how we find that solar weighted reflectance, which tells about the incident photon to the reflected photon ratio. So we are getting those minimum reflectance in the range from 400 to 1000 nanometer. So what I conclude by this study, that copper resisted nano microstructuring of silicon is optimized for different edge path composition by varying the molar concentration of copper salt and H2O2, keeping the temperature constant and time vary the time. So we are getting inverted pyramid like structure in both the cases. And copper catalyst nano microstructured pattern gave 11.88% SWR in case of S-cut silicon wafer, and 16.04% reflectance in case of partial polished. Copper textured inverted pyramid like structure have potential to offer minimum reflectance, and simultaneously it reduces the detrimental effect of the noble metal like silver and gold, etc. So yes, it has potential for solar cell application. Sorry. So I would like to express my sincere gratitude to DST and NPL for the facility and financial support. Thank you. Let's go green with solar.
Thank you, Avriti. I really also appreciate, and I must acknowledge that you kept time. We were going horribly in it, and I'm so thankful to you for keeping it.
Thank you so much.
We can definitely take two questions. I'll just start while others warm up. Can you comment on the choice of copper? Because copper is a known sort of, let's call it a defect in silicon. So is there a reason why you chose copper, and is there a possibility of using some other element in a follow-up study?
So instead of copper, people were using copper and nickel combination, and some sort of that sort of composition for that kind of a structure. But yes, particularly copper assisted etching, we are getting inverted pyramid like structure, because due to the etch rate and due to the position of the copper noble metal, I mean in terms of the what I can say, the
Electrochemical levels. I can sort of see what you're trying to say.
Yes.
Actually, that is where I was going with. So, like, given what does this tell you about what is the possibility of using some other element? So, what would be the desirable properties of or what material properties would you need to look for in a chemical handbook to identify an alternative to copper?
Sorry, sir. I think I'm not able to getting your question.
So supposing I were to go about searching for an alternative to copper, what properties, what material properties should I search for? So you're talking about its oxidation potential, reduction potential, its affinity to silicon. Like, what exactly is the fundamental material property that I would seek if I were to find an alternative to copper?
With the reduction potential.
So I see the reduction potential. Okay, thank you. That's all the question I had.
Okay, thank you.
Is there any other? If there are no other questions, I don't see any in the chat. So in that case, we can thank all the speakers. Thank you. Apologies for the various technical issues, the delayed start as well as the late. Please have a nice tea at your homes, and I think we'll see you in another 10 minutes.
Okay, thank you.
Hello, Vandana, are you there? Hello, Vandana. Anil.
Hello. Hanji sir. Hello.
Vandana.
Yes, sir.
So you logged in, I think, from 3 devices. Can you log out other? The echo will come.
Hello.
I can see your name appearing 3 times.
Yes, sir.
Can you log out? Maybe you are doing from other devices also. That will create a echo.
Okay, okay, sir. Sure, sir. Log out kar दूंगी.
Anyway, it should be ready. We'll start in 2 minutes.
Oh, yes, sir. Yes, sir.
Hello.
Anil, are you there?
Yes, sir. I'm here, sir.
Okay, in 2 minutes we'll start. Okay.
Yeah, sure, sir. Sure.
3:45. Maybe you can share your screen.
Okay, sir.
Presentation.
Sir, is my screen visible?
Yeah. We can see that.
Okay. And my voice is clear. There is no echo and breaking or something.
Yes. Very much clear.
Yeah. Okay, sir. Thanks.
Sorry. बोलोगे ना पीछे आवाज आएगी. इधर देख लोग वहाँ पे आते हैं तो अंदर बैठते हैं. कोई चक्कर नहीं. कहीं बीच में से ना हो गए है ना नहीं बैठे. मेरे को ना अपनी फोटो दिखाना.
Vandana, you mute.
Hello. Yes, sir.
You mute your mic.
Okay.
Okay. Anil, are you ready?
Yes, sir.
Okay. So briefly, Mr. Anil is going to present the effect of different annealing methods on the performance parameters of PSS in silicon junction based solar cells. Okay, go ahead. So you take 12-13 minutes, watch the time and leave some time for question answer. Okay.
Okay, sir. Sure.
Okay.
Thank you so much, sir, for the introduction, and I would like to thank for giving me this opportunity to present my work orally. So today I'm going to present on my work of effect of different annealing methods on the performance parameters of PDOT PSS and silicon solar cells. So I'll do one by one the introduction, which includes why organic silicon and PDOT PSS properties, the basic PDOT PSS and silicon junctions, and the basic optimizations needed to be done before the complete solar cells. Then experimental details of my work, results and discussion, conclusion, and the acknowledgement. So why organic silicon? So in the conventional crystalline silicon solar cells, so it includes high temperature processes, generally greater than 800 degrees Celsius or so, with the complicated instruments and large number of process steps. So which includes overall the high cost of the solar cells.
So while the organics, they do not require costly vacuum deposition equipments and high temperature processes, they can be very easily deposited by solution processes, and can the final solid film can be made by low temperature annealing treatments and so. And there are wide variety of organics which are available, and whose energy levels can be tuned for the requirements which we need along with the absorber layers. So there are few of the organics are there, which are the polyethylene, P3ST, P.PSS, and PCBM, etc. So one of the, apart from these advantages, one of the major disadvantage of these organic semiconductors is that, so the degradation is always there, and this is the one of the common thing that on that the community is working right now. So the P.PSS, it's full form poly 3,4-ethylene dioxychafine polystyrene sulfonate. It's an organic semiconductor which is P-type in nature with band gap of around 1.6 electron volt and work function of 5 electron volt. So it's made of two parts: P dot, which is conductive but insoluble in water, and PSS, which is insulating but soluble in water. When we combine them both, so it will give us the possibility of both the conductivity and the water solubility. And the pristine conductivity of them can be further enhanced by adding co-solvents like DMSO, ethylene glycol, and so on. And the wettability to the silicon surface can be increased by adding Triton and underdex or capstones, because that will help us in improving the passivation to the silicon surface. So the basic selective solar cell, we have absorber layer. So when light shines, so on the one side we have electron transport layer, which allows easy access to electrons, while it offers a barrier for the holes. While on the other side we have hole transport layer, which allows easy access to holes, but offers a barrier for the electrons. And then in this way, we can separate out the two different type of carriers into different contacts, leading to high efficiency solar cells. So the basic P.PSS junction includes a silicon over which we deposit P.PSS. On the front side, we have a metal grid for the front side metal, and on the back side, we have blanket metal. So as we can see in the energy level, so when these are aligned, so P.PSS offers a barrier for the electron flow, will allow the holes to flow very easily. And in the band diagram, so it's a band diagram at thermal equilibrium in dark conditions, we can see due to the barrier at the P.PSS silicon interface, the dark current due to electron is blocked, and that will help us in improve the open circuit voltage. So the basic optimization includes the sheet resistance and spin rate optimizations. So spin rate defines the thickness of P.PSS layer, and thickness is important in the sense that it will define the R sheet and as well as the parasitic absorption, and we have to make a balance between them. We need a low R sheet as well as low parasitic absorption. So for keeping in mind that we have to optimize the spin rate. Secondly, the annealing optimization. So that will be used for making a final solid films, which include the temperature optimization, duration, ambient, and the method of annealing which we are going to use. So in this work, I am going to present these two different kind of methods. Then the front contact optimizations, in which after the sheet resistance is achieved, so we have to optimize the front grid so that we make a balance between the resistance losses and the shading losses due to metal, and along with the contact resistance between front metal grid and the P.PSS, so that we can further reduce the series resistance. And the rear contact optimization includes the contact resistance and as well as the metal work function of the rear side, where we are going to collect the electrons. So I will show in the next slide. So here what we have done is we have done the detailed numerical simulations by changing the electron contact metal work function, and we have done the simulation using Centaurus TCAD. So here 5b is the Schottky barrier height, which we define as the difference between the work function of metal and the electron affinity of the silicon. So -5 values represents the metal work function, which is above the silicon conduction band, while +5b represents the work Schottky barrier and work function with the of the metal, which is in the band gap of the silicon. And so we have assumed a uniform generation rate in the silicon, which is corresponding to a JC value of 26.5 milliampere per centimeter square. And we have varied the 5B value from -0.5 electron volt to 0.5 electron volt. So as we can see in the bottom right figure, so JC values are also almost getting doubled while going from 5B of 0.1 electron volt to 5B of -0.1 electron volt. And the VOC also increases by 130 millivolt while going from 5B of 0.1 electron volt to 5B of minus 0.2 electron volt. And the efficiency trends are similar to those of the short circuit current density. And why is that so? We'll see in the next slide. As you can see here, the psi-s is the band bending which happened at the rear side in the silicon due to the different metal work functions. So negative psi in the negative 5b values represents there is a presence of a back surface field on the rear side, which will oppose the flow of holes and allow easy access to electrons, as can be seen in the density versus 5b plot. At, in the negative 5b, so electron density is maximum and almost constant at the rear side, while the hole density is at minimum. And for positive 5b values, the psi is positive, and the electron density decreases exponentially while the hole density is at maximum, as can be seen in the curve. So which will block the easy access to electrons, as there is a barrier to there and allow easy access to holes. So in overall, we can say that the using the metal with low work function improves the overall performance of P.PSS silicon solar cells. So coming back to the annealing optimizations. So here in the experimental details, we have used N-type DSP double-side polished 1 to 5 ohm centimeter FZ 100 oriented silicon wafers. And the front and back metal are of silver with 1 micrometer thickness in the front side and 400 nanometer in the back side. So P.PSS solution is made by mixing PS 1000 P.PSS with the 5% DMSO to increase the conductivity and 1% Triton 100X to increase the wettability of silicon surface. And the P.PSS was spin coated by using 1000 RPM and 60 seconds as the condition. So after spin coating, the cells were annealed by two different methods. In method 1, 4 samples from R1 to R4 were spin coated one by one and then annealed all together over a hot plate by gradually increasing the temperature from ambient temperature to the annealing temperature, which is 140 degrees. And in the method B, the sample was spin coated and directly kept over hot plate, which is kept at 140 degrees. And both the annealings were done in the nitrogen ambient. And we will see how these two annealing methods affect the performance. So this is the fabrication flow chart. So wafers were RC cleaned and 2% ketchup dip was done before the P.PSS spin coating. Then samples were spin coated and then annealed using two different methods, method A and method B, as explained in the previous slide. Then the thermal evaporation of front and back metal was done, giving us the final solar cell structure. So the dark IV characteristics, as you can see from the curve and the table, so the identity factors are well high in the high bias regime, and also we can see these cells which were annealed by method A gives very good diode characteristics as compared to cell D, which was annealed by method B. But the identity factors and J nodes are very high. So in this regard, the further optimization is indeed possible. So coming to the lighted IV characteristics, as we can see, the JSC values are almost same for all the cells. That is because we have used the same spin speed, which will give us almost same thickness of around 105 nanometer. And so for the cell D, which was annealed using method B, gives highest VOC and fill factor of 540 millivolt and fill factor of 64% respectively. For the cells which were annealed by method A, the VOC increases from 480 millivolt to 520 millivolt, while the fill factor increases from 48% to 60% while going from sample R1 to sample R4. And this difference may be due to the fact that the interface degradation may be happening prior to the annealing, because there is a time delay before the annealing, and that may be the one of the reasons. And the efficiency trends show similar to that of VOC and fill factor. So in conclusion, this undesired time delay between the spin coating and the annealing degrades the overall performance of the solar cell. So coming to the EQ and reflectance, as you can see, the EQ and reflectance of all the cells are almost similar or almost equal. So that proves the fact that the JC values are of same and the thickness of the P.PSS layer is same. So in the shorter wavelength range defines the shows the interface quality of the front side. So as we can see, at the lower wavelengths, the AQEs are of similar. So that shows the fact that P.dot PSS and silicon interface, they could be of similar or comparable properties for all the cells. But we have seen differences in the Lighty-Divey curve in terms of open circuit voltage and fill factor, and that difference may be due to the fact that the Lighty-Divey measurements are high intensity measurement, while EQ and reflectance, they are low intensity measurements. So there may be interface defects becomes more prominent at higher intensity of light. So in conclusion, the influence of annealing and the nature of interface traps towards the open circuit voltage and the fill factor needs further exploration in this regard under the effect of high intensity of light. So in conclusion, we have compared two different annealing methods which was used to prepare P.dot PSS silicon solar cells, and we have found out that direct annealing at the required temperature gives the better performance as compared to the gradual increase in the temperature from ambient conditions. And the P.dot PSS spin coated layer needs to be annealed just after the spin coating to avoid the ill effects on the performance of solar cells in respect to the or in regard to the open circuit voltage and fill factor. And the future scope of this work includes the influence of annealing and nature of interface traps towards the open circuit voltage and the fill factor can be explored further. And the optimizations is indeed possible with respect to dark diode, because we can see that the dark diode in the method B gives worst performance, but in the light IV, that diode gives the best performance. So in this regards, we can do further optimization. And in overall, so detailed characterizations of such annealing conditions can be done, and we can find out the actual what is the which is working out behind this performance degradation in the cells, or the interface degradation which is happening between P.dot PSS and silicon. So I would like to acknowledge UGC for providing me senior research fellowship, and MNRE for supporting through project NCPRE for providing the experimental facilities, and CE and IIT Bombay for providing the experimental facilities. Yeah, thank you so much for being with me. If you have any questions, please ask.
Yes, any questions, please? There are no in the chat box.
I have a question, Vamsi. Can I go?
Yeah, please.
Interesting talk, Anil. Just a question was that can you comment on how do you probe these devices given that P.dot is soft material? And the second question was that have you considered optimizing the thickness of the P.dot, because that will increase your JSC?
Yeah, on that, we can do the cross-sectional SEM or the TEM imaging of the devices. So we are working on that. And for the second part, so thickness do affect the total GSE value, because the parasitic absorption happens as we increase the thickness. So if we, let's say, if we decrease the thickness to 50 nanometer to 60 nanometer or so it comes down, and we can increase the GSE by like 3 to 4 milliamperes very easily.
There's also a sort of an anti-reflection coating type effect that happens. That is one of the reasons that thickness is so popular in the literature. But that's a comment.
Yes. So,
thank you.
Yeah. So with respect to that, so as we can see, the refractive index is around 1.5 or so, and when we calculate with respect to silicon, the anti-reflective, for the P.dot PSS to behave as anti-reflecting coating, also the thickness is around 100 nanometer, but that will give us the parasitic absorption. So we have to optimize between the using as a ATR or the parasitic absorption, and then in that way we can optimize further. Because as we can see, for higher thickness, so it may work as a anti-reflection coating, but parasitic absorption may increase. Yeah.
May I ask one question?
Yeah, sure.
Yeah, please.
Just is it the effect is same on the texture surface as flat surface, or?
So the effect may be slightly different, because in this texture surface there are valleys. So if there is a time delay, there may be a movement of P.dot PSS into the valleys, and that may lead to a further difference in the performance.
Just last question. What is the best diode quality factor you could get?
What is the
Best diode quality factor.
ideality factor best till now I've got is 1.24 till now. Yeah, that's that.
Okay, thank you.
Yeah.
Anil, I have one question.
Yeah, sure,
Right?
sir.
You have done simulations also, right?
Yes, sir.
So leaving that work function, what are the other parameters? Like I think you have achieved 15% in that simulation, if I can see efficiency.
Yes, sir. Yes, sir.
What is that you have considered in that, the simulations, like surface recombination of a silicon?
So yeah, on the front side, I've used 1 microsecond as the interface recombination lifetime. So there I've defined a small region of 5 nanometer and 1 microsecond as the lifetime. Because like when we do the lifetime measurement by depositing period traces on both the sides of the silicon, so we
How
can
much?
easily get we can easily get 200 microsecond of lifetime. And by taking the bulk lifetime of silicon around 1 millisecond or so, we can get around in that order. So by that way we can choose the interface lifetime.
Okay.
Yeah.
For passivation, how much is the thickness you have used?
So the same thickness, 100 nanometer.
100 nano. Okay.
Yeah.
Thank you.
Okay, sir. Thank you.
Okay, Anil. Thank you. Now you can unshare your screen.
Yes, sir.
So next, Vandana, are you ready?
Yes, sir.
Yeah, please share your screen and present. So she is going to talk about the effect of oxygen partial pressure on the energy storage performance of ferroelectric PNJT capacitors.
Yes.
See the screen, Vandana, you need to share it.
Sir, it is connecting. It is connecting.
Okay. Okay.
Yes, sir.
Yeah. Yes, we can see.
Hello.
We can see that.
Yes, sir.
Vandana, 12-13 minutes and then leave some time for question answers.
Sure, sir.
Okay.
A very good afternoon to all of you. First of all, I introduce myself. I am Vandana, PhD research scholar from Department of Physics and Astrophysics, University of Delhi. Today I am presenting my work on the topic effect of oxygen partial pressure on the energy storage properties of niobium doped PZT thin film capacitors. First of all, I will discuss why I am focusing on the PZT based material capacitors. PZT, which is a multi-component material, it is a mixture of the two multi-component materials, which are the lead titanate and the lead zirconate. Amongst which lead titanate is the ferroelectric material. It exhibits the first order phase transition from the cubic phase to tetragonal ferroelectric phase. And lead zirconate is the antiferroelectric material at room temperature. One of the best property of PZT is it has the highest Curie temperature, which has the greater than the 500 degrees Celsius. Now, in the PZT structure, there exhibit the lead atoms are present at the corners and titanium or zirconium atoms are present at the bottom of the unit cell, and oxygen atoms are present at the face centers of the cells. When the temperature of the unit cell or material is greater than the Curie temperature of the material, then it exhibits cubic phase, which is totally centrosymmetric in nature, due to which they exhibit no ferroelectricity and no polarization exit in the material. However, if temperature of the material is less than the Curie temperature, then they exhibit a slightly distortions of the zirconium or titanium atoms with respect to oxygen atoms, such that material exhibit non-centrosymmetric and polarization exhibit in the material. Now, diagram of PZT, they exhibit a morphotic phase boundary, which is generally present in the ratio of 52 to 48 in the zirconium titanium ratio. This morphotic phase boundary is the boundary which separates the ferroelectric phase of the PZT into the two phases, which are the tetragonal phase and the rhombohedral phase. At the morphotic phase boundary, there are the 6 domain states of tetragonal and 8 domain states of rhombohedral exhibit, due to which ferroelectricity is maximum at the morphotic phase boundary. Now, generally work on the boundary which is below morphotic phase boundary or just above morphotic phase boundary, such that the material exhibit tetragonal phase or the rhombohedral phase. But above the Curie temperature, material is totally cubic in nature, which is centrosymmetric in nature, and no ferroelectricity or piezoelectricity exhibit in the material. Now, there are due to presence of high Curie temperature, there are the wide range applications of lead zirconium titanate in the field of cooling devices, in the field of tunable capacitors, memories, in the field of sensors and actuators, in the field of pyroelectric devices, in the field of energy storage devices. Among which cooling devices are totally based on the electrocaloric effect of the PZT. Electrocaloric effect is just reverse of the pyroelectric effect. Amongst which, due to presence of thermal fluctuations in the material, it exhibit the electrocaloric effect and mainly work on the principles of heating and cooling effect. Similar procedure is work on the pyroelectric devices, which are based on the pyroelectric coefficient of the material, which has very high value of PZT. And in the sensors and actuators field, PZT exhibit piezoelectricity in the material. Piezoelectric coefficient of PZT is also very high, due to which it has wide range applications in the sensors and actuators. And applications of PZT are also in the tunable capacitors, memory storage devices, energy storage devices, due to high polarization and due to high dielectric properties of the material. Now, in the presentative work, my main focus is on the applications of energy storage devices of PZT. Why I am focusing on the energy storage devices? Because in the today's world, energy crises are low, and due to limited sources of our energy, we have facing many crises, due to which we are focusing on the energy storage devices using PZT based materials. Now, now, since PZT exhibits very high pyroelectric properties, high piezoelectric properties, ferroelectric properties, then why I am doping niobium in the PZT? Niobium acts as a donor atom in the PZT. Why I am focusing on niobium doping? Because after doping of niobium in the PZT, ferroelectric properties are strongly enhanced, pyroelectric properties are also enhanced, and properties are also enhanced using the donor doping in the PZT, such that we are focusing on the niobium doping, such that ferroelectric properties are enhanced, and we can further use this niobium dot PZT in the energy storage devices. Now, this is the experimental work of niobium dot PZT pellet. First of all, for the fabrications of niobium dot PZT thin films, we have fabricated a 1 inch diameter niobium dot PZT pellet. For the fabrication of PNZT pellet, we have used raw material, lead oxide, zirconium dioxide, dioxide, sodium pentoxide. Using the high-speed ball milling, we have mixed all the solutions such that we got a homogeneous solution. After that, we have dried the solution in oven, and after that, the powder is calcined at a very high temperature such that we get a pure perovskite phase of niobium dot PZT. For the fabrication of 1-inch dia pellet, or for the preparation of thin films of niobium dot PZT, we have fabricated a 1-inch diameter target by using addition of PVA, which is the polyvinyl alcohol, which acts as a binder to bind the particles, and then we sinter the powder at a very high temperature, such that which is the optimized temperature as 1200 degrees Celsius, so such that we have got a 1-inch diameter pellet for the preparation of thin films of niobium dot PZT. Now, for the conformation of niobium dot PZT powder phase, we have done XRD spectra of sintered pellet, and from the XRD spectra, we have clearly seen that the niobium dot PZT is successfully synthesized using the solid state route, and it is also seen that the single phase PZT without any pyrochlore or any secondary phase is obtained after sintering at higher temperature, which is the optimized temperature 1200 degrees Celsius, and all the diffraction peaks of PZT are also well matched with the literature reports. Now, this is the process flow for the preparations of thin films of niobium dot PZT. First of all, we have cleaned the substrate. Substrate cleaning is very crucial step for the depositions of good quality films. So we have used a nickel substrate. Why we have chosen a nickel substrate? Because nickel substrate is a provides very small lattice mismatch with the PZT, such that we got a very good quality film of niobium dot PZT, and also it also acts as a bottom electrode for further characterizations of thin films of PZT. And for the preparations of thin films of PNZT, we have used technique, which is the pulse laser deposition technique is used for the present work. This is the schematic of pulse laser deposition technique. Amongst which this is the deposition chamber, and this is the substrate holder over which we have kept the substrate, and this is the rotating target, and this is the target carousel. This is the plasma plume, which is ablated from the target when a high frequency laser is incident on the target. Then materials, atoms, ions of the materials are ablated, which are confined in a plume, which is known as the plasma plume. This plasma plume is totally straight over the substrate and deposited such that a thin layer of film is deposited using the pulse laser deposition technique. Now, we have synthesized the niobium dot PZT films using pulse laser deposition technique, and we have kept a optimized temperature of 650 degrees Celsius, while we have varied the oxygen partial pressure from 25 millitorr to 75 millitorr. From the X-ray diffraction pattern, we have clearly observed that all the films of niobium dot PZT are polycrystalline in nature, and uh, highly perovskite in nature. From the X-ray diffraction pattern, these two peaks of nickel are seen, which shows that the substrate is present in the films, and also one more is
Vandana, in 2 minutes you have to finish it. Okay?
okay, sir. Okay, sir. From the XRD patterns, it is seen that as the oxygen partial pressure is increased, then the polycrystallinity of the films is improved, and degree of texturing is also improved. And these are the inferences from the XRD results, which has clearly seen that as deposition pressure is increased, then the crystallinity is increased, and the degree of texturing crystallite size is also improved with increase in the oxygen partial pressure. These are the AFM atomic force microscopic images of all the deposited films. From the AFM images, it is seen that the films are completely dense and particles are uniformly distributed in the films. The morphology looked more packed as we increase the partial pressure, and roughness is also calculated from the AFM, and it is seen that the roughness is decreased from 35 nanometer to 10 nanometer as we increase the oxygen partial pressure. These are the cyclic. These are the capacitance versus voltage curves for all the deposited films with different oxygen partial pressure from the CV curves. It is seen that the well-defined butterfly loops are obtained, which indicates fast switching characteristics and ferroelectric polarization, which is shown by the two peaks which are clearly seen from the CV curves, and from the CV plots we can calculate the dielectric constant, which is improved with increase in the oxygen partial pressures. These are the P hysteresis loops for all the films at different pressure. From the P hysteresis loop, it is observed that the saturation polarization and remnant polarization are improved with increase in the pressure. Maximum saturation polarization of 51 microcoulomb per centimeter square is observed for higher deposition pressure niobium dot PZ film. And these are the energy storage parameters for niobium for all the films. From the P hysteresis loop, energy storage density, total energy density, and energy storage efficiency is calculated from the PE loops. From the PE loops of all the films, it is seen that the energy storage efficiency is improved with increase in the pressure from 27 to 73%, and total energy density is increased from 17 joule per centimeter cube to 29.7 joule per centimeter cube with increase in the oxygen partial pressure. Conclusion: it is niobium dot PZT films are successfully synthesized using pulse laser deposition technique. XRD pattern confirms perovskite phase of all films. Well-defined hysteresis loops are observed for which indicates their ferroelectric nature, and remnant and saturation polarization is improved with increase in the partial pressure, and high value of saturation polarization is observed for film which is grown at 75 millitorr, which is results in prominent ferroelectric properties, and these are the wide applications in energy storage devices. Thank you. Thank you very much.
So, any questions? Thank you, Vandana.
Thank you, sir.
Shivani, are you there?
Hello, sir. I'm present.
Yes, please share your screen. So Shivani is going to present a correlation between glass thermal properties and resistive losses during silicon solar cell metallization. Yeah, put in the view mode.
Is it visible now?
Yeah, we can see. Yes, go ahead.
Good afternoon, everyone. I'm Shivani. I'm a PhD student in Metallurgical Engineering and Material Science Department of IIT Bombay. Topic of my presentation is correlation between nature of glass in metallization paste and resistive losses in fabricated silicon solar cell. So outline of my presentation would be, first I'll talk about introduction of silver paste, then how glass is important constituent and what role it plays in solar cell metallization. We'll learn basic concept of printing and firing, and then experimental work carried out in lab, and then I'll discuss subsequent results. So silver paste is screen printed on silicon wafer in a pattern manner over the anti-reflection coating, as we can see in this picture. So this is the main concept of metallization of silicon solar cell. So this metallization step is most expensive process in fabrication of solar cell after the wafer itself. So it costs around 50 to 60% of non-silicon cost of cell fabrication. We'll see the main constituents of silver paste. So the first is, of course, the silicon metal powder. This is the main conducting material in paste, which accounts around 80 to 90% of weight percent of the paste. So this is the functioning phase, and its size and morphology is very important in deciding the contact formation. Second is organics, so dispersants, solvents, thixotrope, and binder, etc. Comes in this category. It is around, it sums up 10 to 15% weight percent of the paste, and And these organics decide the rheological properties required for paste printing. Third is the glass, which is around 1 to 5% in paste. And now, why glass is very important in metallization process of solar cell. So glass powder acts as an inorganic binder to provide adhesion between silver bulk and silicon emitter to ensure stable mechanical contact. We all know that wafer is coated with insulating ARC layer, and to make a contact with silicon emitter, we need to etch out this ARC layer, and glass is responsible for this reaction. The lead oxide present in glass takes part in this reaction. So we should know about the thermal properties of glass, and glass transition temperature is mainly responsible. Glass transition temperature is the temperature above which glass begins to flow or softens. So during firing at higher temperature, glass present in paste starts to show fluid-like behavior, and then it moves towards the silicon emitter. During the cooling of firing cycle, a very thin layer of glass gets deposited at the interface, and this thin glass layer contains reprecipitated silver nanocrystals, which are mainly responsible for the current transport by tunneling through this glass layer. Am I audible, sir? Hello.
Yes, we can hear. Okay, go ahead.
Yeah. So the thickness of this glass layer is extremely important to decide the solar cell performance. We can see this picture here in case A. So there is no electrical contact established because the ARC layer is intact here because of high TG of glass. The glass transition temperature is very high, so glass is not in fluid state during the firing, and it doesn't reach uniformly to the junction. So ARC layer is intact and there is no electrical contact. In case B, this is the ideal situation where small Ag nanocrystals are embedded into very thin glass layer because ARC layer is completely etched here. Case C is showing where high reactivity of glass, and the glass is of very high reactivity because of its lower TG. So glass is very fluid and it overly etches out the ARC layer and penetrates into the junction, causing junction shunting. So this reactivity with ARC layer and the flowing behavior study is extremely important, and PBO present in glass determines its glass transition temperature. The higher the content of PBO in glass, the lower its TG will be. So our objective in this study is to understand the effect of glass transition temperature on contact formation, then identifying a glass composition with optimal TG, and we want to replace this toxic lead oxide with non-toxic material.
Shivani, which slide you are in?
Sir, slide 4.
Oh, it is showing 5 here. I am just worried that the slides are not moving. I am seeing the.
So I'm on roll of glass and metallization paste.
Okay.
Yeah. So this is just going to finish now. So we want to lower down the firing cost by lowering firing temperature. Now I'm on screen printing of silver paste. So this is screen printing is the most widely used technique and which gives the most high throughput for paste printing. And there are certain characteristics the silver paste should exhibit, which makes it suitable for printing. And the main characteristic is shear thinning. So we can see a schematic of screen printer at the top right corner. So what happens first when we are not providing any shear force using squeezy, so paste acts like a solid like behavior it shows, but when we put shear force using the squeezy during screen printing, paste should show a shear thinning behavior where it acts like a liquid like behavior, so it gets easier for it to spread and print on the screen. And then when we stop giving the shear using squeezy, it should retain its shape and it does not spread over, and the line should not spread over the wafer. So it will help in maintaining the high aspect ratio and to minimize the shadow loss. So typically we print around 15 to 20 microns height of this finger, and the width is around 60 to 80 microns. So we can see in this figure, it is showing a pointed tip, which is ensuring that the paste will not flow after we remove the shear force. And in screen printer, we can see paste is kept here for printing. Now, after the printing of paste, to make the electrical contact, we go through the firing, and a typical firing profile is shown here with respect to time and temperature. So first it goes through drying, where solvents dry, then it goes to burnout, where all the organics present in the paste burns out, so only glass and silver are present there. And now at higher temperature, around 500 degree, glass starts to melt, and it starts to move towards the junction, and silver present in paste starts to sinter, and during the cooling down it gets reprecipitated at the interface, and this is how we make contact. And it's done in a conveyor belt furnace which has different temperature zones, which is shown here in this picture. Now the experimental work I did in lab, all the precursors like silver powder and glass is prepared in lab. Pictures are shown here, and the SEM of as prepared silver powder in the size range of 1 to 2 micron is also shown here. Now paste preparation. Paste is prepared after having all the raw material. So we prepare the required paste by providing a shear mixing in a 3-roll mill. Now the trials, printing trials. Two types of paste, A and B, were printed to fabricate devices. So we used around 84% silver loading, and glass is in 8%, and others are organics around in 12%. So here two types of paste are there. So what I mean by two types of paste is that two different kind of glass fields are there in paste A and paste B. So the glass feed used in paste A has a comparatively lower glass transition temperature as compared to paste B. A 25 centimeter square silicon wafers is used with a sheet resistance of around 65 ohms per square, and this is coated with ARC layer. Now a back side is coated with aluminum paste, a commercial aluminum paste, and the front side is coated using two types of the silver paste in a pattern manner. After firing, we did the electrical characterizations. So pictures are showing electroluminescence imaging. So we can see in case of A and B. So B is showing very poor non-uniform electrical contact in case of cell B. And when we see the electrical performance parameters, we can say that the main reason is here is series resistance, very high series resistance of cell B. And after doing the fill factor loss analysis, it is evident that difference in efficiency is because the series resistance is giving 23.6% loss in fill factor of cell B. So to further investigate this, we did a silver and silicon interface also. So we prepared these samples using FIB, focused ion beam, and we analyzed using SEM. So we can see here that in cell A, intact very thin glass layer we can see, which is not very uniform in case of cell B. So above this, we can see the contrast in color showing silver and silicon. And at the higher magnification, we can see the embedded silver nanocrystallites in this glass layer, which is completely not present in case of cell B. So this is the main reason why cell B is showing the poor performance, a thin interface, and so because of higher TG glass used in paste, which is printed on cell B, so it had the very shorter time in the temperature range where it can be fluid. So it does not uniformly cover the interface with ARC on diffuse emitter surface, and the ARC layer is intact here, which is evident from higher series resistance of cell B. It is also seen and reported that because of higher TG, the glass does not fluid and it retains as a residual in bulk Ag and it increases the series resistance there. Summary is that we have correlated the electrical performance of solar cell with the flow behavior of glass during firing. A high TG glass is less flowable during firing and causes high series resistance because of non-uniform distribution of glass at silver silicon interface to perform etching reaction of ARC layer. Glass fed with optimal TG is extremely important to obtain better cell performance, and we believe that by gaining the understanding with this study, we may be able to develop a glass to make contact at a lower firing temperatures. A few experiments are also planned, like interrupted firing to understand the microstructural evolution that is happening at different temperatures, but we couldn't do because of the current situation, but they are in plan and we hope to do them in near future. And I would like to thank NCPRA IIT Bombay for providing fabrication and characterization facilities and TCTD Tata Center for Technology and Design at IIT Bombay for financial support for funding this project. Thank you.
Yes, the paper is open for any questions. Okay, if not, thank you, Shivani, for your
Thank you, sir.
presentation.
Thank you for providing this opportunity. Thank you.
Okay, all the best. So now we'll move to the Kumudni Ganesh.
Yes, sir, I'm here.
Okay, please share. And he's going to talk on silicon perovskite tandem cells yes, simulation approach by using TCAD.
Sir, can you view my screen now?
Yeah, I can see that.
Is my audio clear?
Yes.
Okay, sir, I'm going to start now. Good evening, all. Myself, Kumudini Ganesh. I am a research scholar at IIT Palakkad. My topic for today's presentation is modeling of peroxide silicon tandem solar cells, a TCAD-based approach. This will be the outline of my presentation. To start with the introduction, in recent years, there is a great attention for the development of renewable energy resources as they are abundantly available in nature and they are pollution free. After the discovery of photovoltaic effect, solar cells has attained wide attention for converting solar energy into electricity. The growth of the photovoltaic technology over few years can be studied using National Renewable Energy Laboratory NREL efficiency chart. Firstly comes the wafer-based or first-generation photovoltaic technology, which includes wafer-based crystalline silicon as an active layer in solar cells. And then comes the thin film or the second-generation photovoltaic technology, which includes CIGS, CDTE, and amorphous silicon. Later, we saw emerging third-generation thin film photovoltaic technology, which includes dye-sensitized solar cells, organic solar cells, CZTS, quantum dots and peroxides. So looking into peroxides stem from dye-sensitized solar cells. In 2009, Kojima et al., they used peroxides as dyes in dye-sensitized solar cells and obtained an efficiency of around 3.8%. Later, in 2012, long-term stable and all solid-state peroxide solar cells were designed by replacing a liquid electrolyte with a solid-state hole conductor. Further, the efficiency of the peroxide solar cells can be improved by developing efficient growth methods, passivation techniques, and composition engineering. Over few years, the efficiency of peroxide is increasing from 10% and it is even exceeding 20%. So the take-home message from here is peroxide-based solar cells show rapid improvement in power conversion efficiency compared to other technologies over a short period of time. And the next question is, why are we using peroxides as absorbers in solar cells? If we see the cubic lattice structure of peroxide, it is of the form ABX3. where A is a monovalent cation, B a metal cation, and X an halogen anion. So the peroxide materials that are used in solar cells are of the form organo-inorganic metal halide compound. The peroxide materials having this structure exhibits the following properties. So peroxides with these properties, when they are incorporated in solar devices, leads to high efficiency. Now coming to the typical structure of peroxide solar cell, we have peroxide as an optically active layer, and we have electron transport layer and hole transport layer as the selective charge transport layers. So when light is incident on a peroxide solar cell, photons are absorbed and electron and hole pairs are generated. Based on the energy band alignment, the generated electron and hole pairs are transferred to the selective charge transport layer. So here the band offsets act as an opposition or the barrier for the opposite charge carriers. Finally, the generated electron and hole pair are further transferred to transparent conducting oxide and metal electrode. So here we can say that the band offsets enable effective extraction for the transport of the carriers in peroxide solar cells. Now moving on to why peroxide silicon tandem solar cells. So if we observe here, this is an AM 1.5G sun spectrum. If we take an individual peroxide cell alone, peroxides are an high band gap material. So it absorbs photons of shorter wavelength. And hence, if we take only peroxide, this is the amount of absorption seen, and all other portion is seen as the loss. Now, the main motive is to reduce the amount of the loss in the device. So for that, what can be done is we can combine the peroxide material with a low band gap material like silicon, so that even photons at a longer wavelength can also be absorbed. And by doing so, we can reduce the amount of the loss in the device and obtain a wider absorption in the solar spectrum. So we can say that by using a peroxide silicon tandem solar cell, the performance of the peroxide based solar cells can be improved, and we can obtain a broader absorption of a solar spectrum and hence yield devices with high efficiency. And next question is, why loss analysis is important? If we look at the present record of the power conversion efficiency of the peroxide solar cells, it is behind the radiative limit defined by Shockley-Quisser theory. So which says that the theoretical maximum efficiency is around 33.7%. The assumptions made under Shockley-Quisser limit are perfect absorption above band gap, collection probability for all photo-generated electron hole pair is unity, internal conversion efficiency is 100%, and all the recombinations considered here are radiative. But we also have optical losses and non-radiative recombination losses that causes the parameters to deviate from radiative limit. Hence, it is crucial to analyze the losses in the device and try to minimize it in order to improve the efficiency of peroxide-based solar cells. Now, if we look at the losses in the peroxide-based solar cells, they are mainly classified as optical losses and electrical loss. Optical loss is mainly because of reflection from the device and parasitic absorption, which is the absorption in the stack layers other than optically active layer. And electrical loss, what is electrical loss? So all the photo-generated carriers that are generated as a result of photon absorption do not reach the electrodes and generate current. So on the way they get lost. So this causes electrical loss, which is mainly because of recombination and resistive loss. So here we can say that the major losses in peroxide-based devices are because of optical loss and electrical loss. Now we'll study in detail about what is recombination. So for that we'll look at what is carrier generation and then recombination. Now when a light of a suitable wavelength is incident on a material, the energy of the photons is transferred to electrons. So electrons gains energy and get excited from
Ganesh, I advise you to move to your topic, because you have more slides. Don't say the basics, okay?
Yeah, okay, sir. Okay, yeah. I'll go first. Yeah. Okay, so here we can see that the energy of the photons will be transferred to electrons and they get excited from a lower energy state to a higher energy state. giving rise to generation of electron hole pair, and the electron eventually recombines with an hole, and this recombination can occur in different ways. So firstly, when electron recombines with an hole, if a photon is released, we call it as radiative recombination. And during the recombination process, if it first hops to the defect levels and then recombines with a hole, we call it as a Shockley-Reed-Hall recombination. And when the electron will, instead of giving excess energy in the form of a photon, if it gives to an higher, to the third carrier, and that jumps to an higher energy state and excess energy is released as a phonon. This is Auger recombination. Okay, now coming to the structure and working of a peroxide silicon tandem cell. So here is the structure of a peroxide top cell. So here peroxide is used as an optically active layer, and Spiro as an hole transport, and TiO2 as an electron transport layer. And we have a silicon bottom cell. So to connect the peroxide top cell and a silicon bottom cell, we are using a silicon tunnel junction which connects the peroxide top cell and a silicon bottom cell. So this is a structure of a peroxide silicon tandem cell. Now moving on to the working of peroxide silicon tandem cell. When light is incident on a peroxide silicon tandem cell, peroxide and a crystalline silicon, which are optically active layer, absorbs the photons and generates electron hole pair. Based on the energy band alignment, the generated electron and hole pair are transferred to the respective electrodes as shown here. Now, for the movement of the carriers in between the two cells, means in between top cell and a bottom cell, we are using a silicon tunnel junction. And this tunnel junction enables the tunneling of the electrons from the ETL of the peroxide top cell to the emitter of silicon subcell and vice versa. So by this way, it enables the transport of the carriers between the two subcells. Now in TCAD, for modeling the tunnel junction, we are defining a non-local mesh at this interface which defines the tunneling path for the carriers, and we are also activating the band-to-band tunneling for effective transport of the carriers. And the energy band diagram obtained from the TCAD is also shown here, with where the inside shows the tunnel junction. So by encapsulating this slide, we can say that here the tunnel junction is the one that facilitates the tunneling of the carriers between the two subcells. Now for doing the optical and electrical analysis, we are using a Centaurus TCAD, whose Centaurus workbench is shown here, which is a graphical user interface, and S-Device uses the following physical models to perform the optical and electrical loss analysis. So here we can say that the TCAD simulator is useful for analysis of devices, providing insight into main losses in the structure. Now moving on to the loss analysis of peroxide silicon tandem cell. Firstly, the optical loss. So in order to understand or to study the interdependence of the extinction coefficient of the material on the performance of the device, we perform simulations under two cases. Firstly, for low extinction coefficient for silver nanowires and high extinction coefficient for silver nanowires. So when we used a low extinction coefficient for silver nanowires, this is the normalized reflectance and absorption spectrum. We saw that with a low extinction coefficient for Ag nanowires, the amount of parasitic absorption in the Ag nanowires is less, and we could see more absorption in the optically active layer. While we use an higher extinction coefficient for Ag nanowires, the amount of parasitic absorption in the device increased, which led to less absorption in the optically active layer. So here we can say that by using an Ag nanowire with a low extinction coefficient, they exhibit low parasitic absorption. Now moving on to the electrical loss. So firstly, in a tandem solar cell, the open circuit voltage must be the sum of the open circuit voltage of the peroxide top cell and a silicon bottom cell, because we are connecting peroxide top cell and silicon bottom cell in series. To see this effect and to confirm the proper operation of the tunnel junction, we perform simulations for individual peroxide top cell, silicon cell and our tandem cell under different recombination mechanisms. Firstly, under radiative recombination in dark, we simulated for peroxide top cell, silicon bottom cell and a tandem cell, and similarly under light condition we performed for peroxide cell, top cell, and we obtained a VOC of around 1.1 volt. And for silicon cell we obtained a VOC of around 0.5, and for a tandem cell we obtained 1.6. So here we can see that the VOC of the tandem cell is approximately the sum of the VOC of peroxide top cell and silicon bottom cell.
This confirms the proper operation of the silicon tunnel junction which we are using in between the two cells. And the results from the experimental data was also tabulated. Next, we did under Auger recombination in dark for peroxide, silicon and tandem cell, and similarly in light for peroxide top cell, silicon bottom cell and tandem cell. And the performance parameters were also tabulated under different recombinations. Similarly, under Shockley-Ridal recombination, we obtained the characteristics in dark and in light conditions with the corresponding performance parameters tabulated. So here we can observe that the experimental data chosen from the paper matches closely with our simulation results for AG nanowires with an higher extinction coefficient. Now the electrical loss under low extinction coefficient for AG nanowires was performed under different recombinations similarly as we did for higher extinction coefficient in dark, light, and the performance parameters were tabulated, and similarly for it was performed for Auger recombinations and for SRH recombination. And here we can observe that since we are using a low extinction coefficient for AG nanowires, the amount of parasitic absorption is less and there is more amount of absorption in the optically active layer, and hence we can see the higher current density is high when we use an low extinction coefficient for AG nanowires, and hence efficiency is also seen to be high. Next, we will see the comparison of the current voltage characteristics under different recombination losses. So this is from the experimental paper. Now if we do it for radiative recombination, Auger recombination and SRH recombination, here the main observation is that the Auger recombination shows less significant effect on the losses in the recombination loss in the device. This is because the probability of finding Auger recombination is high only under higher doping concentration and high cell irradiance of around about 1000 suns of illumination. But in our case, we are using 1 sun illumination, and hence we can see that Auger recombination does not show much significant effect on the recombination loss. Whereas the Shockley-Ridal recombination shows the most significant effect, means most loss in the device which affects the VOC of the device. This is because the peroxide crystals exhibit defects like the deep level defects, point defects and halide vacancy, and hence we can see that the trap dominated SRH recombination yields the lowest efficiency compared to all other different recombinations. Now moving on to the summary of our work. So in a nutshell, I would like to conclude by telling that, so we compared the JV characteristics from the experimental device with the simulation results for low extinction coefficient and high extinction coefficient. Here we observed that the JV characteristics from the experimental device matches closely with the simulation results for high extinction coefficient of AG nanowires. So the conclusion from this was, to obtain an enhanced optical response, we should choose the stack materials with a suitable extinction coefficient values. The second conclusion was, the major optical loss in the device is because of parasitic absorption, means the absorption in the layers other than optically active layers, and the second optical loss is because of the reflection from the device. And the third conclusion was, the major electrical loss in the device is because of the trap-assisted SRH recombination, which yields the lowest efficiency when compared to other recombination mechanisms. So finally, to conclude, we can tell that in our present work, we set up a simple TCAD-based framework to understand and model different transport mechanism and losses in peroxide silicon tandem solar cells. I would like to acknowledge Dr. Arvind Ajoy for his useful inputs and IIT Palakkad for providing the Centaurus simulator tool to perform the simulation. And also thank Icee 2020 for giving me an opportunity to present my work. Thank you all for your attention.
Okay, Kumudini. So any so the one question I have is, when you say experiment, means it is from the literature, or you people did the experiments also?
No, sir. Now it is we are taken from the literature.
Literature.
Yeah.
Okay. from the silicon, I see why the current is very low. It is a plain surface you have considered.
Yes, sir. Like we are considered plane surface, and the silicon, whatever I show was the 1 second. Yeah, you are asking about the silicon bottom cell.
Yeah, that current short circuit current is 30 milliampere. So why the message is due to the plain silicon you consider?
Yes, sir. We are using a heterojunction silicon, which is we have an this when the amorphous silicon also sandwiched, and in between amorphous silicon we have an
Okay, the hetero.
crystalline silicon is used as an optically active layer, and we have 1 second. I will do it for- So this is the structure we are using for silicon bottom cell. So we have
Yeah,
a
I think
crystalline.
they are very thin. They're sorry, very thick.
Hmm.
So that's why I think current is a
Yes.
problem. Okay, so why you have selected that there is means tandem of 13%? Try to match up with so that tandem cell is made with a heterojunction.
Yes, sir. This is with an heterojunction. We have an amorphous silicon also.
No, experimental values you have taken.
This measurement details are all from experimental paper.
Experimental paper. The tandem cell consists of a heterojunction, silicon heterojunction.
Yes, sir.
Okay. Kumudini, thank you very much.
Thank you, sir.
Okay, now we'll move to the last presentation. Icee George.
Yes, sir.
Okay, so now please you share your screen. So Icee George is going to present a design of photovoltaic membrane desalination and monitoring system. Yes, we can see that. So now you put in the view mode.
Okay, sir.
Yeah, you can. Yeah, you can continue.
And and for the hot region, we kept 3 different temperatures again. After water, we also you have a then charge level, and it also using the app we could control the switching on and off.
significant impact on improvement of flux, thereby increasing technology.
Okay, and see, so any questions? No questions. So once again, I would like to thank all the speakers of this session and all the best. So now we'll go to the final session and it's going to start around 5:30. Okay, please join us there.
Yes. Audible, sir?
Yeah, Manan, yes, go.
Okay. So first of all, I would like to congratulate Professor Khare, Professor Singh, and all the organizers